So let's begin with the next chapter, that is current electricity, right? So what is a current? We know what is a current, right? So current is defined as the rate of flow of an electric charge. I is equal to what? Q by T. I is the current, Q is the charge flowing through this conductor, suppose, per unit time, okay, divided by time is T, okay. So now there are large number of free electrons inside a conductor, okay, and electrons are moving in random directions. So what we can say is the number of electrons on an average which are moving from left to right is equal to the number of electrons moving from right to left, and therefore the net charge crossing that area would be equal to 0 if there is no potential difference connected across the conductor, right? So when you connect some potential difference, then what happens? The electrons gain a particular direction. So electrons will start moving from negative to positive, and therefore there would be current flowing from positive to negative, okay. So electrons flow from negative to positive terminal. What does so it means that the negative charge is flowing from negative to positive terminal, and we can equally say that the positive charge is moving from positive to negative terminal. So there would be flow of current when we apply some potential difference. And then there is this law called as Ohm's law, which says that the current through the conductor is directly proportional to the potential difference applied across it. That means, suppose when potential difference applied is equal to, let's say, 1 volt and current of 1 ampere flows, then if you increase the potential difference, if you make it 2 volts, the current will also increase, right? It will become 2 amperes, so on and so forth. So V is proportional to I, and the proportionality constant between V and I is called as the resistance of the conductor, okay. It is denoted by R, and it's known as the resistance of the conductor. Now what is resistance? So resistance is the opposition to the flow of current, okay. Resistance is what? It's opposition to the flow of an electric current, okay. So then this resistance, that's the opposition to flow of current, is directly proportional to the length of conductor, and it's inversely proportional to area of cross section. So simply you can think it this way. So where does this opposition come from? It will come from what? Suppose electrons want to move, let's say, from this side to that side, okay. Electrons move from this side to that side. So now more number of electrons are moving from this side to that side, more would be the current, okay. More number of electrons move from this side to that side, more would be the current, you can say, right? So then see, electrons, suppose they come over here and they want to move from right to left. So what will oppose the flow of electrons? There are lots of atoms and ions inside that conductor, right? There are lots of atoms and ions. So these atoms, so electrons, when they collide with the atoms and ions of the conductor, then what will happen? So electron gains some velocity, okay. So when it collides, what happens? It loses its velocity, so you can say it stops, right, momentarily, and therefore its path is opposed, right? So now when it moves, okay, when it moves, let's say through this much length, so let's say n number of atoms will oppose it, okay. Suppose there will be n number of collisions. So when you double the length, what will happen? The collisions will be doubled, right? Okay. So when the length is this much, so there will be certain number of collisions, let's say n number of collisions. Now if you double the length, number of collisions will be doubled, okay. So that's why the opposition is doubled, you can say. So resistance is directly proportional to length, okay. More is the opposition, less will be the current, right? And then what about this thing? Resistance is inversely proportional to the area of cross section. That means if you increase the area of cross section, what will happen? The current will decrease, okay. Sorry, resistance will decrease. Sorry. So when you increase the area of cross section, resistance will decrease and current will increase. Okay, how is it so? So suppose when you connect, let's say this wire, okay, one wire only having some length and some area of cross section across a battery. So certain number of electrons move from this side to this side. Okay, now when you connect identical conductor, let's say this another conductor, okay, like this, so area of cross section is doubled. So now some electrons will flow through this conductor, some number of electrons will flow through this conductor. Okay, if you connect them separately across the same battery, and if you connect them together, then what will happen? The current will be doubled, right? Suppose n number of electrons move from this conductor, okay, when it is connected separately to a battery, and n number of electrons flow through this conductor. Okay, so when you connect the two conductors to the same battery simultaneously, okay, like this, then area of cross section is doubled, right? So n electrons flow from this one, n electrons flow from this one, that means current is doubled. This thing is clear. So current is doubled means what? Resistance becomes half. So that's why we say resistance is inversely proportional to the area of cross section. Is it clear, everyone? Okay. So the resistance is directly proportional to length and it is inversely proportional to the area of cross section. And then if you remove this proportionality sign, put an equality sign, a constant will enter. So that constant is known as the specific resistance or the resistivity. Okay, so R is equal to rho times L by A. This rho is called as the specific resistance, or it is known as resistivity of a conductor. Okay, so because of this thing, the resistance of different conductors is different. Okay, because you can take two identical wires, one made up of copper, one made up of iron, let's say, and the resistance would be different, right? Length is same, area of cross section is same, but then the composition of those two would be different. Okay, the atoms of iron and atoms of copper, they are not identical, their density is also not identical, right? So because of that, what will happen? There will be a different number of collisions, okay, different number of collisions between the atoms and electrons, and that's why you can say the resistance would be different. Okay, so it depends on this factor which is known as resistivity or specific resistance, right? So what is unit of resistance? Unit of resistance is ohm. Okay, unit of potential difference is volt, we have seen that earlier also. Unit of current is ampere. Okay, so what is ohm? Ohm is what? It is a unit of potential difference, that is volt, volt divided by ampere, right? So after that, what would be unit of this thing? So take this ampere on, sorry, area of cross section on this side and length of the length on this side. So unit of length is meter, and you will have meter square in denominator, so that meter square will get cancelled out. I mean the square will get cancelled out. So you have meter divided by meter square. Okay, square gets cancelled out, meter remains. So move it on other side, you get unit of resistivity, so that is ohm meters. Okay, unit of resistivity is ohm meters, right? After that, next thing is conductivity. It's another definition. Conductivity is 1 upon resistivity. Okay, conductivity is what? 1 upon resistivity, right? Next we know the Ohm's law. What is Ohm's law? V is equal to R times I, and then this R can be written as what? Rho into L by A, right? So V is equal to rho times L by A multiplied by I. After that, now you can move this L on this side. Okay, if you move L on this side, what do you get? V upon L is equal to rho times I by A, and then this I by A is called as current density. It's written as J. Okay, I by A is called as current density. And what is V upon L? So it's potential difference per unit length. So we know that it's the electric field. Okay, potential difference per unit length is the electric field. So therefore you get this relation, E is equal to rho times J, or you can write this rho as 1 by sigma, right? And you can move that sigma on other side. So you get J is equal to sigma times E. Okay, so we need to remember all these relations. A lot of relations are coming. Okay, so we need to remember all of them. So E is equal to rho times J, or you can write the same relation as J is equal to sigma times E. Okay, where what is J? J is the current density, current flowing per unit area of cross section, right? Okay, after that, next is the temperature dependence of the resistivity or resistance, you can say. So suppose you have some conductor and its resistance at 0 degree Celsius is R naught. Resistance at some other temperature is suppose RT. Okay, suppose you are increasing the temperature and resistance becomes RT, right? So first of all, why would there be any change in the resistance? So the reason is there are atoms inside the conductor, atoms and ions, you can say. Okay, and those atoms or ions, they are continuously vibrating. Okay, so the vibration depends on what? It depends on the thermal energy that they are getting from the surrounding. So if you increase the temperature, then what will happen? The thermal energy will increase, so they will vibrate faster, right? So then now when electrons move through the conductor, so suppose this is an atom, it's vibrating like this, so electron can move without a collision. Okay, if atom is not vibrating at all, if the atom is vibrating like this, then there is more chance of collision. If it's vibrating faster, okay, so suppose this electron moves like this and atom is vibrating here, so it requires some time to pass through this region. Okay, and now in that much time, if there are more number of vibrations, that means there are more chances of collision, right? If there are more chances of collision when vibrations increase, that means what will happen? The resistance will increase. Okay, resistance increases, right? So that's why the resistance depends on temperature. When temperature increases, resistance will increase. This is for conductors. This is for conductors. Okay, for semiconductors, when you increase the temperature, the resistance will decrease. Okay, and reason for that is in semiconductors, what happens is the atoms are inside the covalent bonds. Okay, and sorry, the electrons are inside the covalent bonds. Okay, atoms are forming covalent bonds and electrons are inside the covalent bonds. So now when you increase the temperature, few electrons, they will gain some energy to come out of covalent bonds and they will be available for conduction. So at 0 Kelvin, none of the electrons are available for conduction. That means it acts like an insulator. When you increase the temperature, then what will happen? The electrons will become available for conduction, and that's why the conductivity will increase. That means resistivity will decrease. Okay, all right. So R naught is resistance at temperature 0 degree Celsius. RT is resistance at temperature T. Delta R is supposed change in the resistance. That is delta R is RT minus R naught. Okay, so this delta R would be directly proportional to R naught. Why is it so? So suppose the original resistance is 100 ohm, then for 10 degree Celsius, suppose there is change of 1 ohm, then if original resistance itself is 200 ohms, okay, so for 10 degree Celsius there is 1% change, suppose. So now what will happen? So what will be the change? Change would be 2 ohms, right? So therefore delta R, the change in resistance, is directly proportional to R naught. Okay, and delta R is also directly proportional to delta T. Okay, more is the change in temperature, more will be the change in resistance, and therefore you can combine these two. So delta R is proportional to R naught delta T, right? And you can write delta R as RT minus R naught, and this proportionality constant here, see, you can remove proportionality sign and put an equality sign, so the constant will enter. That proportionality constant is known as the temperature coefficient of resistance, or resistance temperature coefficient. Now this is alpha, okay, this is not proportionality sign, okay. So RT minus R naught, this is change in resistance, is equal to alpha times R naught delta T, and you can move this R naught on this side, and then you can also take it common from this term and that R naught that's coming on that side. So RT is equal to, you get R naught multiplied by 1 plus alpha delta T. So you need to remember this formula, RT is equal to R naught multiplied by 1 plus alpha delta T, right? Is this thing clear, everyone? Okay, then, so alpha is suppose temperature coefficient of resistance, and conductors have this positive temperature coefficient of resistance. That means alpha is positive for conductors. So as you increase the temperature, the resistance of conductors goes on increasing, okay. So plot of resistance versus temperature, or plot of resistivity versus temperature for conductors, it looks like this. As you increase the temperature, resistance increases. Then semiconductors and insulators have negative temperature coefficients like this, okay. And then there are some materials like nicro, mica, etc. Their temperature coefficient of resistance is very small, okay, it's almost negligible. So as you increase the temperature, there is very small change in the resistance of these kind of materials, okay. There is some change, but the change is very small compared to that of the conductors and the insulators or semiconductors, other semiconductors and insulators, right? Okay, so that resistance changes very less with respect to the temperature. So now what kind of material should be used to produce artificial resistances? Okay, you need artificial resistors in almost all of the devices, all of the electrical and electronic devices. So of course you need some reliability there, okay. As you increase the temperature, the current or functioning of your device should not change, right? So therefore the material that is used to make artificial resistances is nicro, mica, and there is another one, that's carbon, okay. Next, let us see the microscopic understanding of the current, that is the Ohm's law, okay. So suppose you have this conductor and you have not connected any battery across this conductor, so now there won't be any current. So why there is no current? So see, electrons are moving in random directions. There are lots of free electrons, but they are moving in random directions, okay. So therefore now suppose the electrons, some of the electrons are moving like this, some electrons are moving like this electron is moving like this one is moving like this, okay. So suppose u1, u2, u3, so on and so forth up to un are their velocities, u1 bar, u2 bar, okay, up to un bar, before you connect any battery. This is velocity of first electron, this is velocity of second one, this is velocity of nth one. Then since they are moving in random directions, so if you take average of all these velocities, then what will you get? You will get 0. So average of velocities of electrons is equal to 0, means no electrons are crossing any particular cross section, okay. The number of electrons moving from this to this side is equal to the number of electrons moving from this to this side, okay, and therefore there is no flow of current. But now when you connect a battery, that is when you apply some potential difference, or you can say the electric field, okay. So when you apply some electric field, these electrons will experience some force, right? How much force, how much of force will they experience? That is charge on electron multiplied by the electric field, okay. So in vector form you can write the force experienced by electrons is equal to F bar is equal to what? Minus of E times, that is charge on electron, this is minus E times the electric field E bar. Okay, force can be written as mass times acceleration, and that's equal to minus E times E bar, right? And then what would be the acceleration of electrons? Therefore the acceleration of all electrons would be minus of E times E bar, small e times E bar, okay, divided by m. This is the acceleration of electrons. And then now suppose you consider a particular time, okay, and you measure the average velocity now. So suppose an electron collides with an atom, right, and this is an it has got some velocity u1. Okay, the electron is moving with velocity u1. Okay, so first electron is moving with your with the velocity u1. First electron is moving with velocity u1, and then it collided with some atom before time t1. So for how long is it accelerating with this acceleration? For time t1 we can say, right? Second electron, it had collision before time t2, okay, and since then it's moving with velocity u2, okay. So how much of time does it get to accelerate? It gets time equal to t2, right? So then what would be the velocity of first electron now? So v1 bar would be equal to u1 bar plus a times t1, okay, a bar times t1. v2 bar is u2 bar plus a bar times t2. Similarly, you can say velocity of nth electron is un bar plus a bar times tn, right? And now if you take the average, so add up the velocities of all electrons divided by n, the number of electrons, okay. So let's take capital N instead of small n here, because we are going to use small n for something else. Capital N is the number of electrons, okay. So then we have already taken the average before we applied some electric field, so this average is equal to 0, right? The sum of initial velocities divided by n is equal to 0, right? Then now what remains is you have a1 times t1, sorry, a times t1 plus a times t2 plus so on and so forth up to a times tn, and then you can take a common from all those terms, and then what remains is summation, that is sum of t1 t2 t3 so on and so forth up to tn, okay. So this sum of t1 t2 t3 so on and so forth up to tn divided by n can be written as tau. What is tau? Tau is the average relaxation time. What is relaxation time? So electron collided with some atom, okay, let's say time t1 before, and now for time t1 there is no more collision. So electron, if there is no electric field applied, you can say electron is relaxing, right? Okay, or you can just say electron is relaxing because there is no other collision, okay. So average relaxation time is the average time between two successive collisions, okay. So you can write the tau as t1 plus t2 plus t3 so on and so forth up to tn, okay. T suffix n, we need to have capital N everywhere, okay, capital N, capital N, capital N, because there are capital N number of electrons, okay. All right, so then tau is equal to t1 plus t2 plus so on and so forth up to tn divided by n. This is the average time for which the average time that electrons get between two successive collisions, okay. So then you get the average velocity is equal to a bar times this tau, and what is a bar? It is e times small e times capital E divided by m, okay. And therefore this is the average velocity. So this average velocity of electrons is known as the drift velocity, okay. This average velocity with which electrons move inside a conductor, it is known as what? It is known as the drift velocity, Is this thing clear, everyone? Okay. So before you applied any electric field, the average velocity was 0. Now electrons on an average they are moving towards from negative terminal to positive terminal. Okay, and their velocity, this average velocity is known as what? Drift velocity. Okay, so you can say electrons they are moving in random directions, but they are drifting because of the force applied by the electric field or the external potential difference, and that's why on an average their motion is from negative to positive. Okay, so then we have seen that this drift velocity is equal to, in vector form, minus e times tau, minus e times capital E by m into tau. Okay, again we need to remember this. So this thing can be written as Vd is equal to mu times E. Okay, in vector form, Vd bar is equal to mu times E bar, because E is a constant, then mass of electron is a constant, and this average relaxation time, it would be different for different conductors simply because of the composition of conductors. But then if you take one conductor, on an average this average relaxation time would be same at a particular temperature. Okay, average relaxation time would be same at a particular temperature. Okay, and therefore you can say this is a constant. But then see, that constant is written as mu. Mu is the mobility. Okay, so what is mu? Mu is equal to minus E times tau by m, and you can see it depends on what? It depends on tau, right? And tau depends on what? Tau depends on the temperature. So mobility also depends on the temperature. Okay, so there are these small things that we need to understand, right? Okay, so we found that electrons move with velocity called as drift velocity from negative to positive terminal. Okay, after that now consider this conductor. So suppose there are n number of electrons per unit volume. Okay, small n is the number of electrons per unit volume, and then you take some cross section, this much cross section, and because electrons are moving with velocity, average velocity Vd, so some electrons will move from here to here in some time. Okay, in some time, you can take some time, let's say t. Okay, so how much of charge moves from here to here? So we can simply say that when electrons from here, from this cross section, they move till here. Okay, so this much length is L. So electrons are moving through volume what? Through volume, let's say delta V, whatever is the volume between these two cross sections. Okay, because when electrons of here, electrons which were here, they move till here, then electrons which are here, they will move till here. Okay, so electrons in this much volume, they're moving, right, in the time interval t. Okay, so therefore how much of charge moves? So we can say it's charge on one electron multiplied by number of electrons which move through this much volume. Okay, charge on one electron multiplied by the number of electrons that are moving through this much volume. Okay, so how can you find out the number of electrons which are moving through this much volume? So you know the n is the number of electrons per unit volume, just multiply that with this much volume. Okay, so what is this volume? It's area of cross section multiplied by this length. Okay, it's the area of cross section multiplied by the length, right? So charge on an electron is E, number of electrons per unit volume is n, and the volume is equal to A times L. So this gives us the number of electrons which are moving through that volume, and therefore the charge that's moving through that volume in a particular time, let's say t. So Q is equal to E times n multiplied by AL. Is this thing clear? Then just divide both sides by time. okay, and if you divide it by time, so you get this length through which the electrons move divided by the time. And what's that? It is the average velocity of the electrons, right? It's the drift velocity. And what's q by t? The charge crossing some cross-sectional area per unit time is the current. So you get I is equal to E times N into A Vd, or I like to say it this way, NEAVD, okay, NEAVD, right? And this is the microscopic equation for the Ohm's law. Okay, we'll understand how. Okay, so we need to remember this relation, I is equal to NEAVD, right? Let me write it like this, NEAVD. Okay, then so let's remember this one. Then we can substitute Vd is equal to, I will just substitute the magnitude of this. Vd is E times E by m, okay, lowercase e times uppercase e means charge on electrons times the electric field divided by m. Substitute that here times tau, okay, E times E by m into tau. Then what do you get? You get I is equal to E times, okay, EA, sorry, N times EA, right, multiplied by this thing, Vd is E times E by m into tau, right? So you get, okay, if you multiply this out, you get NE square tau by m multiplied by A into E, right? NE square tau by m multiplied by A into E. And what is E? So E is, you know, it's V divided by L. The electric field is equal to potential difference per unit length. So you put that over here or over here. So what do you get? You get I is equal to NE square tau by m multiplied by A by L into V, right? And now you can move these things on other side. So you get V is equal to m upon NE square tau times L by A multiplied by I. Okay, V is equal to m by NE square tau times L by A multiplied by I. Now what is this thing? So this is your standard form of Ohm's law of V is equal to R into I, right? You can see that this thing is equal to what? This thing, if you call it rho, then you have V is equal to rho times L by A. That means this would be the resistance, okay, resistance multiplied by current. So what is this thing? This thing must be the resistivity. What is resistivity then? Rho is equal to m divided by NE square tau. Okay, resistivity is equal to m divided by NE square tau, right? Is this thing clear? So this equation is equivalent to Ohm's law. Okay, we haven't done anything, we have just substituted the Vd is equal to this thing, E times E by m into tau, and we have substituted that E is equal to V by L, right? So this equation is equivalent to Ohm's law. Okay, now again we get what? We get the equation for resistivity, and that is m by NE square tau, okay, from microscopic understanding of the Ohm's law. Is this in clear? Okay, good. So we need to remember this thing, okay, rho is equal to m by NE square tau, we need to remember. All right, so now lot of equations, let's see some problems based upon this thing. The resistance of a platinum wire at 0 degree Celsius is 2 ohms and 6.8 ohm at 80 degrees Celsius. The temperature coefficient of resistance of wire is, this was asked in 2023, NEET 2023, and very simple question, right? Based upon the formula, RT is equal to what? R naught multiplied by 1 plus alpha delta T, right? We want to find out alpha. So what is RT? It is 6.8. R naught is 2 ohms multiplied by, you have 1 plus, we need to find out alpha, but then what is change in temperature? Change in temperature is 80. Okay, move this 2 on other side, so this is 6.8 divided by 2 is 3.4, 3.4 is equal to 1 plus 80 alpha. Then it's very simple. So just move this 1 on this side. So it's 2.4. 2.4 is 80 alpha. And therefore what is alpha? It's 2.4 divided by 80. Right? Or we can write this thing as, okay, let me multiply by 100. So this thing becomes what? I will multiply and divide by 100. This thing becomes 240. 240 by 80 times 10 raised to minus 2. So this thing will, this thing is 3 then. 3 multiplied by 10 raised to minus 2. Okay, so that's the answer. Okay, per degree Celsius. Right, so it is option C. Very simple question. Okay, so this is from some other exam, RS 2022. The reciprocal of resistances. Tell me. Conductance, reactance, mobility, conductivity. Question should be like this. Okay, it's option A, conductance. Good. Reciprocal of resistance is conductance. Right? Let's see next one. This is from NEET 2022. Okay. As the temperature increases, the electrical resistance decreases for both conductors and semiconductors, increases for conductors but decreases for, option B, increases for conductors but decreases for semiconductor. Good, that's correct. Right, resistance of conductors will increase, but for semiconductors the resistance will decrease. Okay, so very simple. This is from NEET 2022. Okay, this one is also from NEET 2022. So let's see this one. Copper wire of length 10 meters and radius 10 raised to minus 2 divided by root of pi has electrical resistance of 10 ohm. The current density in the wire for an electric field strength of 10 volts per meter is. Okay, tell me. Copper wire, its length is given, radius is given, right? Means length is given, radius means you can say area of cross section is given, A is equal to pi r square, we know. Okay, and resistance is also given, R is given. Okay, R is equal to 10 ohms, right? And electric field is given, that's 10. So the question is, what is the current density? What is the current density? What's the formula? J is equal to sigma times E, right? Or we can say E is equal to rho times J. Right, this is the formula. Okay, E is equal to rho times J. But do we have rho? We don't have rho. Rho can be written, right? E is equal to rho times J is the formula. So question is, what is J? Okay. Now you have this relation R is equal to rho times L by A, and we don't know rho, but we know R, we know length, and we know area of cross section. So we can substitute for rho. Okay. So that is, what will be rho? R times A upon L. Right. But then we want J, current density is asked. So just move these things on other side. Okay, L times R by A on this side, L times R by, sorry, L divided by R by A, move it on this side. So multiplied by, you have electric field, L by RA. Okay, so that is L by pi r square. So let me write here itself pi r square. So now put the values. Okay, so what is length? Length is 10 meters. What is resistance? Resistance is also 10, right? Resistance is also 10. What is pi? Pi is pi. Okay, r square. So that means you have this thing square, radius square. So 10 raised to minus 2 divided by root pi square. Okay, it's 10 raised to minus 2 divided by square root of pi square. 10 raised to minus 2 by root of pi square. and then you have electric field. How much is electric field? Electric field is also 10. So root pi square and this pi will get cancelled out. Okay, so this thing gets cancelled out. 10 gets cancelled out. What remains is 10 raised to minus 2 square, so that is 10 raised to minus 4. In numerator it will be 10 raised to right, 10 raised to 1 plus 10 raised to 4, that means 10 raised to 5. Okay, so answer is 10 raised to 5, right? So it is option C. Okay, so this one is from NEET 2022, right? So at least some formulas are, I mean, there are questions based on some formulas, right? This one is clear. Okay, good. Let's see next one. So this is from NEET 2021. Okay, not that old. And here you can see this question is based on, see, if you remember all formulas, then only you can solve question like this one. Okay, so that's why formulas are important. So column 1 gives the certain physical terms associated with flow of current through a metallic conductor. Column 2 gives some mathematical relations involving electrical quantities. Okay, match column 1 and column 2 with appropriate relations. Okay, drift velocity. Do we have relation for drift velocity here? So we remember that drift velocity is equal to, it is equal to what? It is a times tau, right? So you can see tau here, and what is a? So e times e by m multiplied by tau. Okay, this is drift velocity. So a is option, I mean a matches with 3. Okay, so let me write a matches with 3. Then electrical resistivity. So if you remember, resistivity is what? M divided by Ne square tau. Okay, and similar formula for conductivity would be Ne square tau by M, right? So M divided by Ne square tau, is it there? It's not there. Okay, then we don't need this one. There is one formula in terms of the electric field and the current density. Okay, if you remember, J can be, or E can be written as rho times J. That means rho is equal to E divided by J, right? So B matches with 4. Okay, A matches with 3, B matches with 4. Okay, I will write it here. A matches with 3 and B matches with 4. Okay, so then A with 3, B with 4, A with 3, B with 4. So still there are two options, right? We need to check for C. So relaxation period, okay, that is tau. What's the formula for that? Okay, so 3 and 4 are gone. Is it NEVD? It's not that, right? Because it is for current density, right? I is equal to, you know, NEVD. If you move A on this side, okay, A on this side, then you will get J, which is I by A, is equal to NEVD, because you have moved A on this side, right? So this one matches with this one, that is D matches with 2. So it's option B. Okay, D matches with 2. So it has to be option B. Then let's check the remaining one. What's the remaining one? Remaining one is relaxation period. So it has to be this one. Yes, we know this formula, no? Rho is equal to Ne square tau by M, right? So rho is equal to Ne square tau divided by M. Sorry, rho is equal to M divided by Ne square tau. I was writing equation for conductivity. m divided by n square tau, and you want tau, so move tau on this side, rho on this side, so you will get tau is equal to what? This thing implies that tau is equal to m divided by n square rho, right? N e square rho. So that's correct. Okay. So C matches with 1. Okay, that's why it is option B. Is this one clear? Okay, so here see, we need to remember all of the formulas, right? Okay, good. Let's see next one. The resistance of a wire is R ohm. If it is melted and stretched to n times its original length, its new resistance will be. Tell me. If it is stretched, okay, what will be its new resistance? If wire is stretched n times, it's option B, n square R. Good. Okay, so just remember this, that if wire is stretched n times, its new resistance will be n square times R. Okay, how is it so? So let me explain, because everybody might not know. So we know, see, you have a wire, when you stretch it, so we'll assume that its volume remains constant. Okay, so volume remains constant. So therefore, initial area, original area is suppose A, original length is L, and then or let's say A1 L1, and then final area and final length, suppose A2 and L2, right? So volume is area multiplied by length. Okay, so from here you get ratio of L1 is to L2, or let's take L2 is to L1, would be equal to what? L2 by L1 is A1 by A2, it's A1 by A2, and if it is stretched n times, then that means that L2 by L1 is equal to what? It's equal to n. This is equal to n. Okay, and then what is resistance? So if I want to take ratio of R2 by R1, then we know resistance is equal to what? I will write it here, R2 by R1. So resistance is rho times L by A. So R2 is rho times L2 by A2, and I want to divide by R1, so that is rho times L1 divided by A1. Okay, so dividing by this thing is multiplied by its reciprocal, so right, rho times L by A dividing by rho times L by A is multiplying by its reciprocal, so we have multiplied by A by rho L. Okay, so rho gets cancelled, rho gets cancelled. What remains is L2 by L1. Okay, so L2 by L1 times A1 by A2, and L2 by L1 is n, and A1 by A2 is also n. That means this is n times n, so this becomes what? N square. So therefore you have R2 is equal to n square times R1. Okay, this is clear? Yes, Nikita, Silva Kumar. Okay, good.
Clear, sir.
Good. So then let's see next one. A wire of resistance 4 ohm is stretched to twice its original length. The resistance of stretched wire would be, yeah, so it's option B, right? N square times. Okay, stretched stretched to what? Twice the original length. That means n is equal to 2. So use the formula. R2 is n square times of R1. Okay, so n is 2, and therefore this would be equal to what? 16 ohms. Okay, so it is option B. So see, this question is repeated. Okay, See next one, a wire of certain material is stretched slowly by 10%. Okay, its new resistance and specific resistance becomes respectively. Tell me. So see, option A says both remain same. We know resistance changes, but specific resistance will remain same. You are not changing material of wire, right? So it's option D, right? Good. It's option D, good. So option A is not correct. Okay, both remain same, it's saying. All right, let's see next one. A 6-volt battery is connected to terminals of 3-meter long wire of uniform thickness and resistance of 100 ohm. The difference of potential between 2 points on the wire separated by a distance of 50 centimeter will be. Tell me. 6-volt battery is connected to a wire. Okay, this is the wire and the battery that you have connected. Okay, battery that you have connected, it has potential difference of 6 volt. Okay, and its resistance is 100 ohm. Resistance of this wire is 100 ohm. So now the potential difference between 2 points on the wire separated by a distance of 50 centimeter will be. So this is simple. See, what will be potential difference between these 2 points A and B? They are separated by 3 meters. Okay, A and B are separated by 3 meters. So then the potential difference between them is 6 volts, right? That is the applied potential difference. Okay, and then if you take 2 points which are separated, so let's say I take a point over here, okay, in half of the length, then what would be potential difference between these 2 points? So potential difference between these two is 6 volts. Potential difference between these two must be 3 volts. Okay, potential difference between these two must be 3 volts, right? Because I have taken half of the length. Okay, so how much of length are you taking? You are taking 50 centimeters and the length of wire is 3 meters. So 50 centimeter is equal to what? 1/6 of the length, right? And that's why the potential difference between the points separated by 50 centimeters would be equal to what? It would be equal to 1/6 of the total potential difference. So that is 1 volt. Is it clear? Or shall I explain it in some other way? Not clear? Alright, see this. So we know V is equal to I times R. Okay, V is equal to I times R. That is, now some current flows through this wire. Okay, then it can be written as I times rho L by A. Okay, so now for this wire, I is a constant, rho is a constant, area of cross section is a constant, right? Once you have connected the wire, I is constant. Okay, area of cross section of wire and rho, it's a constant. So you can say that V is directly proportional to L. Okay, V is directly proportional to L. So now if 6 volt battery is applied to terminals of this wire having length equal to what? 3 meters. Okay, then potential difference between these 2 points separated by a length of 3 meters is what? 6 volts, and V is directly proportional to length. So if you take just 50 centimeter of length, how much would be the potential difference? It would be 1 volt. How? So you can say, let's say VAB, okay, divided by V is equal to LAB divided by the length that we are taking. Okay, we want to find out V, right? So this is 6, right? 6 volts. divided by V is equal to, what is LAB? So length of the wire is 3 meters and this is 50 centimeters. That means 50 into 10 raised to minus 2. Okay, move that 10 raised to minus 2 on this side in the numerator. So this thing becomes 300, right? So 300 divided by 50 gives you 6. Okay, and therefore what do you get? V is equal to, that 6 and 6 will get cancelled out. V is equal to 1 volt. This is clear. The potential difference between 2 points of a wire is directly proportional to what? The length. Okay, so that way you can solve it simply. All right, let's see next one. Copper and silicon is cooled from 300 Kelvin to 60 Kelvin. The specific resistance. Tell me. This is very simple. Copper is a conductor, silicon is semiconductor. Option A decreases in copper but increases in silicon. Good, that's correct. If you increase the temperature, the resistance of conductors increases. Okay, but for semiconductors it will decrease, right? So it decreases in copper but increases in silicon. That's correct. Let's see next one. Specific resistance of a conductor increases with increase in temperature. Okay, that is also simple. Let's see next one. This is from NEET 2020. Solids which have a negative temperature coefficient of resistance are metals, insulators, semiconductors. Insulators and semiconductors. Which one is correct? Option D. Good. Okay, very simple question. This one also from NEET 2020. Which of the following graph represents the variation of resistivity with temperature for copper? Is it A, B, C, D? Option C. Good. It seems like 2020 was simple. Good. Option C. Let's see next one. A conducting wire of cross-sectional area of 1 centimeter square has 3 multiplied by 10 raised to 3 charge carriers per meter cube. Okay, charge carriers means electrons. Okay, if the wire carries a current of 24 milliamperes, then drift velocity of carriers is. Okay, what is the drift velocity? This is question. So you know that I is equal to, right, NEA VD. You have this formula. I is equal to NEA VD. Okay, we want VD. VD is equal to I divided by NEA. Okay, simple question, right? Because current is given, area of cross section is given, A is given, and charge carriers per meter cube, that means small n is also given. So just put the values. I is 24 milliamperes, so 24 multiplied by 10 raised to minus 3 divided by n is 3 multiplied by 10 raised to 23. Then what else? Charge on electron is 1.6 multiplied by 10 raised to minus 19, and area of cross section is 1 centimeter square, that means 1 multiplied by 10 raised to minus 4 meter square, right? You need to convert it to the SI unit. Okay, and then carry out the division. So 24 divided by 3 is 8, so that's 8 divided by 1.6. Okay, times 10 raised to minus 3, this is 10 raised to 23. Okay, 10 raised to minus 19 minus 4 is 10 raised to minus 23. Minus 23 plus 23 cancels out, and what remains is this thing, 10 raised to minus 3. Okay, so 8 divided by 1.6, I can write this thing as 80 divided by 16. So that's 5, right? So the answer is 5 multiplied by 10 raised to minus 3 meters per second. Okay, so it is option C, 5 multiplied by 10 raised to minus 3, right? This is simple. Next is series and parallel combination of resistors. Okay, so now suppose you connect n number of resistors or n wires in series combination, and their resistances are R1, R2, R3, so on and so forth, right? So then now see, when you apply some battery, some current will flow through them. Okay, so the applied potential difference is V. What would be potential difference across this first one? It will be current multiplied by resistance of this one, I times R1. Potential difference across second one is I times R2. Potential difference across third one, I times R3. And if you add up the potential difference across R1, R2 and R3, you will get the applied potential difference. So V is equal to V1 potential difference across R1, V2 potential difference across R2, and V3 is potential difference across R3. So V is equal to V1 plus V2 plus V3. Okay, very simple. Then V can be written as the current flowing through these resistors. Now see, electrons, they are moving suppose in this path. Okay, so they have to move through R1, R2 as well as R3. Okay, so same current will flow through R1, R2, R3 because they are connected in series. Okay, so path of electrons is same, right? So therefore current is same, that is I. So you can write this V, the applied potential difference, as the current multiplied by total resistance of these ones. So that is RS. RS is R suffix S. It is the series combination, resistance of series combination, right? And that can be written as I times R1 plus I times R2, right? V1, V2 and V3, and then you can cancel out I. Okay, so this is very basic, right? So then we get RS is equal to R1 plus R2 plus R3. Okay, that's very simple. And I think this relation, the series and parallel combination, it has been taught earlier also in some standard 10th or something like that, right? Anyways, so RS is equal to R1 plus R2 plus R3. This is clear? Okay, good. I think you remember that. Okay, and when you connect resistors in parallel, then what happens? So you have connected these resistors in parallel. So see, what is series combination? When only one terminal is connected. Okay, you have R1 and R2. They are in series, means one terminal will be common between them. Okay, what is parallel? If both terminals are common, that is parallel combination, right? So here two terminals are connected. This is parallel combination. Okay, so R1, R2, R3 are in parallel, and you have connected this battery. Okay, so or a cell having potential difference of V volts. Okay, so then all of these resistors, they are connected across this battery, right? So potential difference for all of them will be equal, but then current will be different. Okay, current will be different, right? Because suppose some electrons come from here to here, so at this point they have three paths along which they can move, right? So electrons can move along this path or this path. Okay, so then that means there are three possible paths for current to flow, and therefore current will get divided into three parts. Okay, so current will be I1, I2 and I3, right? So electrons move from this to this side and current moves from the other side, right? Okay, so what happens is current gets divided into three parts. Okay, current gets divided into three parts. Current through R1 is I1, current through R2 is I2, current through R3 is I3. Okay, but what we can say is the total current is I, and it's equal to I1 plus I2 plus I3. Then suppose total resistance of this combination is Rp, because they are connected in parallel, so suffix P. So the current can be written as potential difference divided by total resistance, so that is Rp, and it's equal to current through R1, that's V upon R1, right? Potential difference divided by resistance. Current through R2 is V upon R2, current through R3 is V upon R3, and then you can just cancel out V, and what do you get? You get 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Very, very simple. If there are n resistors, this thing will follow. Okay, so it will be 1 by R1 plus 1 by R2 plus 1 by R3, so on and so forth up to 1 by Rn, right? So this is very simple, and I guess you already know these relations. Okay, then now if you have two resistors R1 and R2, they are connected in parallel, then the equivalent resistance, just remember this, it's R1 R2 divided by R1 plus R2. If there are only two resistors connected in parallel, then equivalent resistance is R1 R2 divided by R1 plus R2. How? So you can just solve this. 1 by Rp is equal to 1 by R1 plus 1 by R2, and you will get this thing. Okay, so it's very simple. Then now this is important relation. Suppose the current flowing through this thing, okay, through combination of these two resistors is I. Then the current splits into two parts, I1 and I2. I1 is current through R1 and I2 is current through R2. Okay, so total current is I. So what will be current through R1? So current through R1 is equal to, remember this, it's I1. I1 is equal to R2 divided by R1 plus R2 multiplied by I. Okay, so we can solve. How does it come? But we'll just remember this formula, that current is equal to R2 divided by R1 plus R2 multiplied by I. Okay, and what will be current through R2? So current through R2, the second resistor, will be equal to first resistance R1, okay, R1 divided by R1 plus R2 multiplied by I. Okay, are these formulas clear? I1 is equal to R2 divided by R1 plus R2 times I, and I2 will be equal to R1 divided by R1 plus R2 times I. Okay, so that's very simple, right? Yes, no? Okay, good. So please remember these formulas. Okay, and then if there are n resistors, n identical resistors connected in series, then their total resistance is equal to n times of R. If they are connected in parallel, the total resistance is equal to R divided by n. Okay, n resistors connected in series, identical resistors, total resistance is n times R. If they are connected in parallel, then the total resistance is R divided by n. Okay, and one more thing, that the formulas for capacitors and the resistors connected in series and parallel, they are opposite to each other. Okay, so you must have guessed that earlier itself, right, when we saw the formulas for capacitors. Okay, so for capacitors in series combination, it's 1 by Cs is equal to 1 by C1 plus 1 by C2 plus so on and so forth. And in parallel combination, Cp is equal to what? C1 plus C2 plus so on and so forth up to Cn, right? So it's opposite for capacitors and resistors, right? Please remember that. And then we'll see the electromotive force. Okay, so this is an important concept. Now electromotive force is not a force, so this is a misnomer. Okay, electromotive force, but they had again already named it, so you cannot change it. Okay, so scientists had named it already, thinking of when you connect some battery, what happens, some force is applied on the conductors, etc. Okay, so the quantity that they are calling electromotive force is not force, actually it is the voltage. Voltage means what? Okay, we'll call it EMF only, but it's voltage. Voltage means potential difference. Okay, so now what is EMF? EMF will be denoted by this letter epsilon, or will denote it by E, right? So it is open circuit potential difference across the cell. So we have this cell and it's open circuit, means it's two terminals, negative and positive, they are not connected to each other. Okay, they are not connected to each other, okay, by a wire. They are not short. This thing is called as shorting. Shorting means what? Just connecting the two terminals, okay, or even through the external resistance, open circuit. Then the potential difference across them, the positive and negative terminals, it is known as EMF. Okay, then there is another definition of EMF. What is potential difference between 2 points? So we had studied this in electrostatics, that is the work done per unit charge to conduct that charge from one point to another point. Okay, if you remember, work done per unit charge to conduct that charge from one point to another point. So now suppose you have this cell, okay, so this is the small r is part of cell, okay, and you have connected that to this external R, this resistor. Then what's the potential difference across the resistor? It is the work done per unit charge to move that charge across the resistor, right? It's the work done per unit charge to move that charge across the resistor. Or if you think about the battery, okay, so let's see here, what's potential difference between these 2 points or between the positive and negative terminals? It's the work done per unit charge to move a charge from positive to negative terminal of battery. Okay, that is terminal potential difference. Terminal means between the ends, okay, terminal potential difference. Then what is EMF? So EMF is work done per unit charge to conduct the charge once round the complete circuit. Complete circuit means internal circuit as well as external circuit. Okay, internal circuit as well as external circuit. So potential difference is work done per unit charge to move the charge once round only external circuit from positive to negative terminal. That's why it is called as potential difference or terminal potential difference. But what is EMF? Work done per unit charge to move that charge once round the complete circuit. That means suppose charge is starting from positive terminal of battery. Okay, positive charge starts from positive terminal of battery. It comes to the positive terminal. So it moves through external resistance as well as through the battery. Okay, so then the work done per unit charge is known as EMF, right? The internal resistance of battery would be very small, okay, but still there would be some resistance. So we draw a battery like this. This is a symbol of battery, so or a cell. So it will have some EMF denoted by epsilon or E, capital E, right, and some internal resistance. So the small r shows the internal resistance of the battery, okay, and this battery or the cell, it's connected across this external resistance or some wire, let's say. So now what is EMF? So just like we write V is equal to I times R, here the EMF, see, this is work done to move a charge once round the external circuit only or external resistance only. It can be written as I times R. Now when you move a charge once round the complete circuit, that means through external resistance as well as internal resistance, then what would be work done per unit charge? So it is I times external resistance as well as the internal resistance. So I times R plus R, okay, and therefore you can write this EMF as I times capital R plus I times small r. And what is I times capital R? So you know that that is the terminal potential difference, the potential difference across the external resistance, or you can say potential difference across the end points of this battery. End points means positive and negative terminal, okay, but there is a difference in this case, in the definition of EMF, and in this case here the current is flowing through, here the current is flowing through what? The battery, right? Battery is supplying some current, okay, so you can say that EMF is equal to voltage, terminal potential difference is also known as voltage, okay, plus I times small r, and therefore you get V is equal to V is the terminal potential difference, it's equal to EMF minus I times small r. Okay, so we need to remember these formulas, right? This is clear, everyone? Okay, good. So then next is combination of cells. So if you connect n cells in series, what will be the resultant EMF and what will be the resultant equivalent resistance? So this is the relation. If you connect n cells in series combination, okay, total EMF will be just sum of individual EMFs of all of the cells. So ES is just equal to E1 plus E2 plus E3, so on and so forth. Okay, and right, and then what will be the internal resistance? So internal resistance is also, because you are connecting them in series, so it's just sum of the internal resistances. So just remember this formula. Okay, and it's just like common sense. Okay, when you connect batteries in series, the potential difference will get added up, right? Potential difference gets added up. Okay, so that's why potential difference gets added up means what? EMF gets added up. Okay, is this thing clear, or do I need to explain the derivation for this? Derivation means, actually, see, suppose you have these two cells connected in series. So what is potential difference between points A and C? It can be written as potential difference between the points A and B plus the potential difference between points B and C, right? Potential difference between A and C can be written as potential difference between A and B plus the potential difference between B and C. Okay, and what is potential difference? So we have seen that it's equal to EMF minus current times the internal resistance. Okay, so here you have connected two cells. Okay, between these 2 points, two cells are connected, and this circuit is this combination is connected to some external resistance, suppose. So some current will flow. Okay, current is suppose I, and because they are connected in series, current will be same. So now suppose total EMF of this combination is ES. Okay, total resistance of the combination, internal resistance, is RS. So you can say the potential difference between these 2 points A and C is equal to what? Potential difference between A and C is total EMF minus current into total resistance. Okay, and that can be written as potential difference between A and B. So there is only one cell, right? So potential difference is EMF minus I into R. Okay, what is there between points A and B? First cell, its EMF is E1, then internal resistance is R1, so potential difference is E1 minus I into R1, and potential difference between B and C is E2 minus I into R2. And now if you compare this side with this side, what we get is EMF is just equal to E1 plus E2, right? Then compare the internal resistances, the terms containing internal resistances, so you get minus I times Rs is equal to minus I times, you can combine these two, R1 plus R2, and that minus I gets cancelled out, so you get Rs is equal to R1 plus R2. This is clear. Similarly, we have combination of cells in parallel. Okay, so here, see, here you will have two cells in parallel. So suppose some current, this combination provides some current. Okay, current should be, actually the direction of current should be opposite. This combination provides some current, suppose. So current is I. Okay, then suppose E1 provides current I1, E2 provides current I2. So sum of those two is equal to I, we can say. So I is equal to I1 plus I2. And suppose EP is the EMF of this parallel combination, right? EP is the EMF of parallel combination. RP is the equivalent resistance of the parallel combination. Okay, then we can just write that what would be the potential difference between these 2 points. Potential difference between these 2 points. So it's suppose V. So how much would be I? How much is I? So I is equal to, so if you see this relation, okay, if you see this relation, this one or this one, so just move V on this side, okay, so you get E minus V, and move R on that side upon R is equal to current, right? So current is equal to E minus V by R. Okay, this is clear? Yes, no? Okay, good. So here the equivalent EMF is suppose EP. Okay, the potential difference is same between these 2 points or across this battery or across this battery. Potential difference is same. Potential difference is V. Okay, and then so this current can be written as what? I1 plus I2. What will be I1? So I1 is just E1 minus the potential difference V divided by this internal resistance R1. What will be I2? E2 minus V divided by internal resistance R2. Okay, and then what we can do is we can separate the terms containing EMF and potential difference. So what do we get? So see, EP by RP would be equal to E1 by R1 plus E2 by R2. Okay, and what is RP? So RP is just equivalent resistance of this parallel combination, right? So 1 by RP is equal to 1 by R1 plus 1 by R2. Okay, is this thing clear? Is this formula clear, everyone? Okay, so we need to remember this formula. So series is simple. In parallel, what happens? The equivalent EMF divided by the equivalent resistance of parallel combination is equal to sum of the ratio of EMFs to equivalent resistances. Okay, EMFs to, sorry, I said equivalent, EMFs to internal resistances. Okay, so the ratio of total EMF to total internal resistance in parallel combination is just equal to the sum of ratios of EMF to internal resistances connected in parallel combination. Okay, EMFs to internal resistances of the cells connected in parallel combination. Okay, so remember it this way, right? Okay, good. So then let us see some problems based upon these things. Okay, so two metal wires of identical dimensions are connected in series. If sigma 1 and sigma 2 are the conductivities of metal wires respectively, the effective conductivity of the combination is, tell me. There are two wires connected in series and they have identical dimensions. So the length is same, area of cross section is same. Okay, so you connect two wires, right, having identical dimensions. So you have connected them. Sigma 1 and sigma 2 are their conductivities. Okay, what we can say is total resistance is equal to R1 plus R2, right? And how can you write the total resistance? So Rs is equal to, I can say, rho s, okay, multiplied by total length. So length of first one is suppose L, length of second one is L. So total length is 2 times of L, but area of cross section is A, right? Area of cross section is A, and that's equal to rho times L by A, rho 1 times L by A. and plus rho 2 times L by A. So L by A, L by A, L by A gets cancelled out, right? But you are not asked about the resistivity, option C. Okay, let's check. So what they are asking is about the conductivities. Okay, so what remains is 2 times rho s. So rho can be written as 1 by sigma, right? So it's 2 by sigma s is equal to 1 by rho 1, sorry, 1 by sigma 1 plus 1 by sigma 2. And then if we solve this, what will we get? So you can make the denominator same, it's sigma 1 sigma 2, right? Then multiply this term with sigma 2, the other term with sigma 1, that's 2 by sigma s, and then take reciprocal and move 2 on this side. So sigma s is equal to 2 times of sigma 1 sigma 2 divided by sigma 1 plus sigma 2. This is simple. Okay, it's option C. This is clear. Okay, good. Let's see next one. A wire of resistance 12 ohm per meter is bent to form a complete circle of radius 10 centimeters. The resistance between its two diametrically opposite points A and B as shown in the figure is. Tell me. There is a wire whose resistance is 12 ohms per meter. Okay, so what's given here? Its resistance per unit length is 12 ohms per meter, and therefore what would be resistance? It's 12 times length of the wire, right? What's the length? Length is 2 pi r, and then okay, length of the wire is 2 pi r. Now you have bent it in circle. Okay, so how much of length is there between points A and B? So it's like you have connected two wires in parallel combination, right? This is like two wires connected in parallel combination. Okay, and original length was L of one wire. When you connect it like this, so length of this part is L by 2, length of this part is also L by 2. So resistance of this one will be R by 2, resistance of this part is also R by 2. Okay, right? And R by 2 and R by 2 are connected. They are connected what? In the parallel combination, and therefore what will be the total resistance? Total resistance is Rp, which will be the resistance connected in parallel. Okay, they are identical, and therefore the equivalent resistance will be what? One resistance divided by the number of resistances. So that is R by 2 divided by how many resistances? 2 resistors. 2 resistors are connected, so it will be R by 4, right? So it is R by 4. But what is R? R is equal to 12 times of L. You have 12 times of L divided by 4, and that is Rp is equal to 3 times of L. Okay, so what is length? Length is 2 pi r, so just put that 3 times of 2 pi r, and radius is 10 centimeters, so just put that. So 3 times of 2 is 6, 6 times pi multiplied by 10 centimeters, so it's 10 multiplied by 10 raised to minus 2 meters, that is 10 raised to minus 1. So 6 pi times 10 raised to minus 1, so it's 0.6 pi, right? It's 0.6 pi ohms. Option D, very simple. Okay, so now you can remember this. If there is a wire having resistance R, if it is bent and a circle is formed, and then if you take diametrically opposite points, resistance will be what? resistance between those 2 points will be just R by 4. Okay, resistance will be R by 4. So the question is repeated, that's why I'm asking you to memorize it. So when a wire of a uniform cross section A, length L and resistance R is bent into a complete circle, the resistance between any two diametrically opposite points will be what? It will be R by 4, right? It's very simple. Okay, let's see next question. In a circuit shown, current through 4 ohm resistor is 1 ampere, current through this one is 1 ampere. When points P and M are connected to a DC voltage source, P and M are connected to DC voltage source, right? Then the potential difference between points M and N, what's the potential difference between M and N? Okay, so for that we'll need to find out what's the current through this one. Once we find what's the current, then we can find out potential difference between M and N. Okay, so what's given? Current through the 4 ohm resistance is 1 ampere. Okay, so if you see this, current through this one is given. How much is that? It's 1 ampere. Now you see the points P and M, and there is only, if you take this path, so there is only this resistor connected between points P and M. This one is parallel, right? So current through this one is 1 ampere and the resistance is 4 ohm. So what would be the potential difference across it? It is 4 times 1, right? Current into resistance. So the potential difference V is equal to 1 into 4, that is 4 volts, right? That's simple. So that's potential difference across this resistor, and you can see one end of this resistor is connected to P, other end is connected to M. So same is the potential difference across points P and M. Okay, so I can say potential difference potential difference PD between P and M, what's that? So V, or let's just say V is equal to current multiplied by resistance. Okay, so that's 1 into 4, so it's 4 volts, right? Then we want to find out potential difference across this 1 ohm resistance. So for that, what should we do? We want to find out current in this branch, right? So for that, let's find out the equivalent resistance here. Okay, you can call that branch anything. Okay, so let's just find out equivalent resistance. So let's call this one R1, this is R2, this is R3, right? You can see R1, R2 and R3. So R1 and R2 are in parallel. Okay, so let me call this branch 2 or something, right? This one is branch 2. Actually it splits in this branch again, but let's just say this total is branch 2. Okay, so what is resistance of branch 2? So it is R1 is in parallel with R2, so total resistance is, let's say, R, so it's R1 parallel R2, it's written like this. Okay, parallel, symbol for parallel, plus R3, right? This is R1, this is R2, this is R3. Can you see that? This is R1, this is R2, this is R3. Okay, R1 is in parallel with R2 and then R3 is in series. Okay, so this is R1 R2 divided by R1 plus R2 plus R3. So what's that? So it is 0.5 0.5. Oh, no need to do all that. These two are identical, right? So therefore it's 0.5 0.5 means the resistance of parallel combination will be 0.25. Okay, it is just half of that. Plus you have 1 ohm. Okay, R3 is 1. So this is 1.25. R is equal to 1.25. Therefore what would be the current? Therefore current in branch 2, okay, current in branch 2, or I will just say current in branch 2 is I, or you can call it I prime. Let's say I prime, okay, because we call this one as I, and let's call this resistance also as R prime. Okay, so I prime is equal to the voltage, total potential difference is 4 volts divided by the resistance R prime. Okay, how much is that? So it's 4 divided by 1.25. Okay, 4 divided by 1.25, or okay, so we need to divide this 4 divided by 1.25. So it's should be greater than 3, I guess, but less than what? Less than 4, of course. Okay, and then what would be the voltage across R3? This is our R3, right? This is our R3. Okay, so potential difference across R3 is just, it's equal to I prime times R3, and that's 4 by 1.25 multiplied by 1. How much is that? It's greater than 3, right? So 3.2. Yes, so this is clear. So let's see this next problem. Two cells having same EMF are connected in series through an external resistance R. Cells have internal resistance R1 and R2. Internal resistance is R1 and R2. R1 is greater than R2 respectively. When the circuit is closed, the potential difference across first cell is 0. The value of R is, okay, so you have two cells and they have the same EMF. They are connected in series, okay, and their internal resistance is R1 and R2. So this is given. EMF of two cells is same, right? EMF is equal, but internal resistances are R1 and R2, and then they are connected to some external resistance capital R, okay, like this. And after that, what's given? Then when circuit is closed, so circuit is closed, then the potential difference across first cell is 0. Okay, potential difference across this first cell is 0. So suppose some current I flows through this circuit, then what is potential difference across the first cell? So it is V1. V1 is equal to E minus I times R1, right? And this is equal to 0, they say. So E minus IR1 is equal to 0, and from that what do you get? I times R1 is equal to E, or I is equal to E divided by R1. Okay, then next is, from this circuit you can find out the value of I. What will be I? So I is equal to total EMF, that's 2 times E divided by total resistance. So what's total resistance? R1 plus R2 plus R. R1 plus R2 plus capital R, and this I and this I should be equal, right? So that is, you have 2 times E, okay, E upon R1 is equal to 2 times E divided by R1 plus R2 plus R. So E gets cancelled out, okay, E gets cancelled out. So what remains is 2 times R1 is equal to R1 plus R2 plus R. So 2 times R1 is equal to R1 plus R2 plus R, and you can move that R1 plus R2 on this side. So 2R1 minus R1 is R1. Then you have R1 minus R2 is equal to R, right? Sorry, this is capital R, no? Okay, so R is equal to R1 minus R2. It's very simple. Yes, no? It's option B. Okay, let us see next one. A battery consists of a variable number n of identical cells having internal resistances RH, which are connected in series. So there is a battery which consists of variable number of cells and internal resistances R. The terminals of battery are short circuited. Okay, so you just connect the terminals of battery. Then the current I is measured. Which of the graph, it's option A, which of the graphs shows the correct relationship between I and N? Right, that's correct. Okay, because if you connect n number of cells in series, okay, they are connected in series, n number of cells in series, what will be the EMF? This is first cell, then second cell, so on and so forth. So EMF, net EMF would be equal to n times of E. And what will be net resistance? So net resistance will be equal to what? N times of R. Okay, so then what will be the current if you just short circuit them? The current will be equal to net EMF divided by net resistance. So that is E times of R, sorry, n times of E divided by n times of R, and n gets cancelled. Okay, so what remains is E divided by R. So when you connect n one cell or n cells, the current will remain same. Okay, so therefore it is option A. So that is also simple. Let us see next one. A current of 2 ampere flows through a 2 ohm resistor when connected across a battery. The same battery supplies a current of 0.5 amperes when connected across a 9 ohm resistor. So first you connect a battery to a 2 ohm resistor. So this is 2 ohm resistor. And the question is, what is the internal resistance of the battery? The internal resistance of the battery is, so first you connect the battery to this 2 ohm resistance. Okay, then you connect it to second resistance, which is 9 ohm, right, which is 9 ohm, the same battery. So in first case you get a current of 2 amperes, and in second case you get a current of 0.5 amperes. Okay, so the question is, what is the internal resistance of the battery? So see, in first case, how can you write the current? So I1 is equal to, let me write it here, I1 is equal to E divided by R1 plus small r, you can say, right? So that's equal to, I1 is 2 amperes, so that is 2 divided by capital R1 is 2 ohms plus small r. Okay, we can cross multiply this. Right, okay, sorry, EMF is not given, no, EMF is not given. A current of 2 ampere flows through a 2 ohm resistance when connected to across a battery. The same, yeah, EMF is not given, otherwise there won't be anything in the question. So EMF is E only. So you have 2 is equal to E divided by 2 plus R. Okay, or you can move that 2 plus R on other side. So you can write, or we can write it like this: E is equal to I multiplied by R1 plus small r. Okay, for the first case, or I1 multiplied by R1 plus small r. What is I1? I1 is 2 amperes. Okay, what is R1? R1 is 2 plus small r. So this is your first equation from this one. And then from this one you can write E is equal to what? I2 multiplied by R2 plus small r. Okay, and what is I2? So I2 is equal to 0.5 multiplied by R2 is equal to 9 ohm, 9 ohm plus small r. Okay, so this is your second equation, and it's the same EMF. That's why first equation, I mean the left hand side is same, so right hand side must be same. So therefore what do you get? You get 2 times of 2 plus small r is equal to 0.5 times of 0.5 times of 9 plus small r. Okay, then just multiply it out and you will get the answer. So it is 4 plus 2r is equal to 9 times 0.5 is 4.5, 4.5 plus 0.5 r, right? So then move this thing on other side. So it is 2r minus 0.5 r, so that is 1.5 r is equal to 4.5 minus 4 is 0.5. Therefore what will be r? 0.5 divided by 1.5 or 5 by 15 you can say. Okay, so that's 1 by 3. So the answer is 1 by 3 ohm, right? So again we just have to compare two equations and solve this. So this is also simple. A cell having an EMF E and internal resistance R is connected across a variable external resistance capital R. Okay, as the resistance R is increased, the plot of potential difference V across R, okay, V versus R is given by. So tell me what will be the answer? Okay, so we know this. See, E is equal to V plus I into R, right? We want V, no? So V is equal to E minus IR. Okay, then what is I? So if you have, suppose this external resistance and this one is variable, right? You can change it. This is the symbol for variable resistance. Okay, you can change it and you are increasing it. So this is your battery and this is suppose internal resistance. So how much would be the current? I is equal to E divided by R plus small r. Now you can put that over here. So what do we get? We get V is equal to E minus E divided by R plus R multiplied by small r, right? And now if you keep on increasing capital R, okay, suppose you start from 0 and you increase it to infinity. Okay, so if this thing becomes infinity, then what will happen? So initially if R is 0, then what will be the current? So this E and, okay, what happens then? This R and R gets cancelled out. Okay, R is 0, then what do you get? E minus E, and that's equal to 0. That means the graph starts at 0, right? The graph starts at 0. Okay, so this one or this one should be the answer. But after that, see, when R becomes infinity, then what will happen? In second term would be equal to 0, right? When R is infinity, that means the denominator is infinity, so numerator is whatever, this term will become 0. Okay, so at R equal to infinity, V will become equal to E. At max, V can become equal to what? The EMF. Okay, so that means the V will not keep on increasing with respect to R. What will happen? At R equal to 0, V is 0. Okay, but then it keeps on increasing and it saturates at what? It saturates at E. That means the maximum value of voltage, terminal voltage, is equal to what? EMF. Is this thing clear, everyone? That's why the answer is option C. Okay, everyone, is it clear? All right, good. Let's see next one. The internal resistance of a 2.1 volt cell which gives a current of 0.2 amperes through a resistance of 10 ohm is. Again, this is similar kind of question, right? And these questions are, I mean, if you can solve one, you can solve all, right? So the internal resistance, we want to find out the internal resistance. Okay, right? EMF is given, current is given, and external resistance is given. So you have EMF is equal to what? I multiplied by capital R plus small r. Okay, so that is 2.1 is equal to 0.2 multiplied by capital R is 10, small r is small r. We want to find it out. Okay, so then just multiply this out. So this becomes 2, right? 0.2 multiplied by 10 is 2 times 0.2 r, and then we can multiply whole equation by 10. So this becomes 21. 21 is equal to 20 plus 2r. Okay, 21 is equal to 20 plus 2r, and then just move this 20 on other side. So you have 21 minus 20 is 1. 1 is equal to 2r. So r is equal to 1 by 2. So r is equal to 1 by 2 means 0.5. Okay, so it's option D. Very simple, right? Okay, let's see next one. A set of n equal resistors of value r each are connected in series to a battery of EMF E and internal resistance R. So you connect n resistors in series. Okay, 1 2 3 so on and so forth up to n in series. Then what will be the total resistance of this combination? Rs is equal to what? N times R, we know that. Okay, and then it's connected to a battery which has EMF equals to E and internal resistance is also capital R. Okay, internal resistance is also capital R. Then current drawn is I. In this case, the current drawn is I. Now, if n resistors are connected in parallel to the same battery, okay, n resistors are now connected in parallel to the same battery, then the current drawn from the battery becomes 10I. Now it becomes 10I. So what's the value of n? Okay, the value of n is, so again this is simple question. You connect n resistors in series and you connect that combination to what? A battery having EMF E and internal resistance is equal to what? Capital R. So what will be the current in this case? They say it's I. Okay, so that I would be equal to E divided by Rs plus this resistance R. Okay, Rs plus R, that means n times of R plus R, right? So this is the first case given in the question. Second case is you connect these resistors in parallel. Okay, you connect these resistors in parallel. So 1 2 3 so on and so forth up to n resistors in parallel. Okay, and then you have this battery. So this parallel combination, it will have resistance equal to Rp, and what's Rp? Rp is equal to R divided by N, right? N resistors in parallel, then Rp is equal to R divided by N. We know that. Okay, it's connected in series with this thing, right? These all are in parallel. Okay, but this parallel combination will have some resistance. Suppose it is this much. It is in series with this resistor. Okay, that parallel combination is in series with this one, right? and therefore what will be the total resistance in this case? It will be Rp plus R. Okay, it's Rp plus R. And then in this case, what will be the current? Current, they say it's 10 I, right? It is 10 I. So 10 I is equal to what? E divided by Rp plus R. Now what we can do here is we can multiply the first equation by 10, right? Multiply first equation by 10 and equate it to second one, because this is 1 I, this is 10 I. Okay, right? So let's multiply equation 1 by 10. So from that, what do we get? 10E divided by Rs plus R is equal to E divided by Rp plus R. Okay, and E gets cancelled out, and then what remains is 10 times of Rp plus R is equal to Rs plus R, right? And then we can substitute values of Rp and Rs. So we have 10 times of Rp plus R is equal to Rs plus R. That is, we have 10 times of what is Rp? It's R by N, plus 10 times of R is equal to Rs is Nr plus R. Okay, so then sustain R, take this R on this side, so it will be 9R. So 9R is equal to, you have 10 times of R by N, okay, plus Nr, and actually you could cancel out R in the earlier step itself, but let's cancel it out now. So then it will be quadratic equation, I guess. So multiply this whole thing by n. So what do we get? 9n is equal to 10 plus n square. Okay, or it's n square minus 9n plus 10 is equal to 0. What will be n? Tell me. Okay, so we can factor this out. So it will be n square minus 10n plus n plus 10 is equal to 0. Did I do some mistake somewhere? Yes, I have, right? Okay, this will be negative on that side, no? It will be negative on that side, right? Yes, it will be negative. So this is minus 10, this is minus 10, and then we can factor it out. N square minus 10n, yeah, then the product will be equal to minus 10. Okay, right? So there was a mistake of negative sign. Okay, then we can factor out this equation like this: n square minus 10n plus n minus 10 is equal to 0, right? Okay, minus 10 times 1 is equal to minus 10, right? And then what do we get is n times n minus 10 plus 1 times n minus 10 is equal to 0, and that means n plus 1 or n minus 10 is equal to 0. Okay, if we take n minus 10 common, then what remains is n plus 1. So either n is equal to minus 1, right? Either this term is 0 or this term is 0. That means either n is equal to minus 1 or n is equal to 10. So n equals to minus 1 is not possible, right? So n would be equal to 10. Okay, so answer is 10. This is clear. Okay, good. So again, there is nothing in the question. There are just two cases. We need to compare them and solve, right? After that, let's see the next topic. Next topic is Joule's law of heating. Okay, Joule's law of heating. So when you connect some, let's say a wire to a battery, okay, or you connect a bulb to a battery, what happens? After some time you can see the wire will become hot, okay, or the bulb will become hot, right? So suppose bulb glows for some time, it becomes hot. So what does that mean? The electrical energy gets converted to heat energy. Okay, electrical energy gets converted to what? Heat energy, right? So why is it so? It's because of when current flows in the circuit, electrons move, okay, and they constantly collide with atoms, so they transfer their kinetic energy to the atoms, and that's why the atoms will vibrate with higher velocities, right? The energy of atoms will increase, and that's why the wire will become hot. Okay, so kinetic energy of atoms, vibrating atoms, increases. Okay, so then there is a law called as Joule's law of heating, and it tells us how much of heat would be produced. Okay, so amount of heat generated in a conductor is given by H is equal to I square RT. Okay, simple law. Suppose R is the resistance, I is the current flowing through that resistance, and T is the time for which the current is flowing. Then the heat generated in that resistor is equal to what? I square RT. Okay, so there is very simple explanation to that. So I is current, R is the resistance, and T is time. Then now when suppose charge Q moves through the potential difference of V volts, okay, then what is the work done? So we know that work done is equal to what? V times Q. Okay, so to move that charge you need to do some work, and work done is equal to what? V times Q, and Q can be written as IT, so that means work done is equal to VIT. Okay, and then you can substitute V is equal to IR in this equation, and you get work done is equal to what? If you substitute V is equal to IR, so it is IR times IT, so it's I square RT. Okay, so that much is work done. So now that work is done means what? Some energy is supplied by the battery, and that energy gets converted to what? The energy gets converted to heat. Okay, and therefore the heat developed is equal to what? I square RT. So very simple, right? So then this heat developed can be written in various ways. So one form is this one, VIT. Okay, sorry. Then now we know what is power. So power delivered by the battery would be equal to the amount of work done by the battery divided by the time, right? Power is equal to work done divided by time. So P is equal to I square RT divided by T, and then you can cancel out this T with T. So what do we get? Power delivered by the battery, or power which is consumed in an electrical circuit, it's equal to what? I square R. Okay, it is also called as power dissipated, because once the electrical energy gets converted to heat energy, it's not coming back, so it is power dissipated, right? So P is equal to what? I square R. Okay, you get another formula. So P is equal to this I square R can be written as V times I, right? You have I square R, so it can be written as I times R multiplied by I, right? And IR is equal to V, we know that. Okay, so power is equal to V times I. This is another formula. And then you can write I is equal to V upon R. You can substitute that, and we get this another formula for power. P is equal to V square by R. So now you need to remember all of these formulas, this one as well as this one, okay, because in different scenario uh, different formulas would be used. Okay, for an example, if you have a series combination, then current in the series is same for all components, that is all resistances or whatever you connect in series combination. Then power dissipated, the appropriate formula in that case would be equal to what? I square R. Okay, then if you have a parallel combination, then V will be same. Okay, V will be a constant, right? And suppose you want to compare the power dissipated in various resistors, then the appropriate formula in that case would be equal to what? V square by R. Okay, and again, then depending on the questions, we should be able to identify which formula to be used. Okay, is this thing clear, everyone? It's a very small topic, but there have been a lot of questions asked based on this one. All right, so let's see some questions based upon this thing. This one is from NEET 2022. Two resistors of resistance 100 ohm and 200 ohm are connected in parallel in an electrical circuit. The ratio of the thermal energy developed in 100 ohm to that of 200 ohm in the given time is. Tell me, they are connected in parallel. Okay, so what will be ratio of H1 to H2? So what is H1? It is V square by R1 times T, right? What will be H2? V square by R2 times T. Okay, so they are in parallel. So in that case, heat dissipated would be inversely proportional to R. Okay, heat is inversely proportional to R, right? So what will be H1 is to H2, because V is same and the thermal energy is dissipated for the same time. So H1 is to H2 would be just equal to what? R2 is to R1, right? Because V is constant, T is constant. And then what are the values of R1 and R2? 100 and 200. Just put that. So R1 is 100, R2 is 200. 200 by 100 is 2 by 1. 2 is to 1. Okay. Very simple question, right? Yes, no. Okay. Good. Let us see next one. Okay. Very few times you will get this kind of question where you just have to compare, right? Anyways, let's see next one. A current of 3 ampere flows through the 2 ohm resistor. Current of 3 ampere flows through 2 ohm resistor. It's here, right? The power dissipated in the 5 ohm resistor is power dissipated in this one, 5 ohm resistor. Okay, can you see that? So current of how much? 3 ampere flows through this one, 3 amperes. Okay, so let's say this point is A, this point is B. So what will be the potential difference between points A and B? So all these three are connected in parallel, right? So potential difference in this branch, in this branch, in this branch would be equal. Okay, so what will be the potential difference? V is equal to current multiplied by this resistance. Okay, and same would be the potential difference in this branch also, right? So you can say V between A and B, VAB will be equal to what? Current I, current given, times the resistance. Okay, so let's just put the values. Current is 3 amperes times the resistance is 2, because this current is flowing through this 2 ohm resistance. So the potential difference is 6 volts, right? Potential difference is 6 volts. And then if you consider this branch, third branch, so here also the potential difference is same. We want to find out the power dissipated in this one, so we can just find out the current. Okay, just find out current in this branch, right? So what will be current in the third branch? Let's say this is third branch. Okay, so current in third branch, I would be equal to what? Potential difference VAB divided by resistance, total resistance in that branch. Okay, so that is equal to 6 divided by 1 plus 5. Okay, 1 plus 5, right? So that is 6. So the current would be equal to 6 by 6 means 1 ampere. So I is equal to 1 ampere, and you got current. So therefore what would be the power? What would be the power? Power in that 5 ohm resistor would be equal to I square R. Okay, so that is 1 square multiplied by 5, so it is 5 watts. Okay, so answer is option B. Is this thing clear? Now would you say that this is parallel combination and we have used this formula? Okay, so see, when you want to compare, in that case the formula to be used would be V square by R, but here we don't want to compare, right? We want to find the power in this one. Okay, so depending upon the question we need to think about the formula, right? So what can we find out? Okay, what is given, what we can find out. So what's given? The current in this one is given, so from that what we can find out is the voltage, the potential difference in this resistor. And then we see that this resistor and they, all of them, they are in parallel combination. There are 3 branches, so the potential difference in all of them will be equal, right? So now what you can find out using V square by R in this case, the total power dissipated in this branch, because you already found out V was 6 volt, so you could find total power dissipated in this branch, right, using this formula V square by R. Okay, but you wanted to find out power in this resistor only, and there are 2. Okay, there are 2 of them, 1 ohm and 5 ohm. So better thing to do is just find out current in this branch, and then power in this one would be I square times this resistance. Power in this one would be I square times this resistance. This is clear? Yes, no? Is there any doubt? Okay, Nikita, is it clear? Okay, good. All right. See next one. Power dissipated across 8 ohm resistor in the circuit shown here is 2 watt. Okay, so here R is equal to 8 ohms. So power dissipated in that one is 2 watt. The power dissipated in, yeah, tell me Nikita, wanted to say something? Okay, no problem. Okay, so let's see this one. Power dissipated across the 8 ohm resistor in the circuit shown here is 2 watt. Okay, so in this one the power dissipated is 2 watt, right? then the power dissipated in watt units, okay, across 3 ohm resistor is, again, what would be the power dissipated in this one? Okay, so this is the question, right? Suppose some current I flows in the circuit. It gets splitted in two parts, I1 over here and I2 over here. Okay, right? So then what we can do is we can find out, either there are two ways, either we can find out the potential difference, okay, because power is given, or we can find out the current. Okay, so we can find out the potential difference or we can find out current. So power is given, power in 8 watt is given, so we can say it's V square divided by R. We can make use of this formula, right? So what is that? It's 2 watt, and therefore what will be V square? So V square is power multiplied by the resistance. Okay, so power is 2 and the resistance is 8, so that means V square is 16. So what would be V? So V is equal to 4 volts. Okay, so we got the value of the potential difference across this branch, it's equal to 4 volts, right? Same would be potential difference across this branch also, okay, because they are in parallel combination, and therefore what you can say is I1 multiplied by 3 plus 1, that's the total resistance in this branch, it's equal to the potential difference. Okay, so potential difference is 4, right? So what would be I1? So 3 plus 1 is 4, move that on other side, so I1 is equal to, you get 4 by 4, 1 ampere, right? So you got I1, current in this branch is 1 ampere, right? And then, okay, then what would be the power dissipated in this one? It is just I square R. Okay, so power in 3 ohm resistor is just equal to what? I1 square multiplied by 3. So that is 1 multiplied by 3. So 3 watt, right? So answer is option A. This one is clear. See next one. Total power dissipated in watt in the circuit shown here is. So again, this is very simple. We want total power dissipated in this circuit. So just find out total resistance. So 6 and 3, they are in parallel. Okay, so their total resistance would be what? Total resistance of these two, let's call it Rp. That Rp would be in series combination with this 4, right? So what is Rp? So Rp is, we know, R1 R2 divided by R1 plus R2. This is our formula. Okay, and what are those R1 and R2? So 6 and 3. So it is 6 times 3 divided by 6 plus 3 means 18 divided by 9. So that is 2 ohm, and that the resistance of these two is 2 ohm. Okay, so we can replace this thing by a 2 ohm resistance, and the 2 ohm comes in series with this one, right? So your circuit will get modified like this. This is 2 ohm resistance, this is Rp, and then you have this 4 ohm resistance, and then you have this battery. Okay, right? So battery has potential difference of 18 volts. Okay, so then what will be the total resistance? So R total, or you can say that is, these two will be in series combination. So Rs is equal to what? It is equal to 2 plus 4. 2 plus 4 means 6 ohms, right? And then, okay, then you got the resistance, total resistance in the circuit, and you have the potential difference. So you can just make use of V square by R formula. Okay, so power dissipated would be equal to V square divided by RS. Okay, so V square is 18 square divided by, you have 6, so that is 18 times 18 divided by 6, and 18 by 6 is 3, 18 times this 3 is 54, right? So it's 54 watt. Okay, another simple question, right? Okay, so see next one, power, this is also based on power. Okay, see this one, 6 similar bulbs are connected as shown in the figure with a DC source of EMF E and 0 internal resistance. So internal resistance of this one is 0. Okay, the ratio of power consumed by the bulbs when all are glowing, okay, all these bulbs are glowing, and in situation when 2 from section A, so this is section A, and 1 from section B, this is section B, are glowing, will be. So what is the power dissipated in this first case versus the second case where just 2 of these are glowing and 1 from these are glowing? Okay, so in first case we'll just replace the bulbs by the resistance of bulb, right? So this is R, this is R, this is R, these three are connected in parallel, you can say. This is again R, 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 they are connected in parallel. So what will be resistance of this branch? It will be, sorry, this section, R by 3, right? Because there are 3 resistors connected in parallel. So R, R and R. So total resistance will be R by 3, and resistance of this section would be equal to R by 3. So this R by 3 and this R by 3 is in series combination, right? This R by 3 and this R by 3 would be in series combination. It's in series combination, right? So therefore what would be the total resistance? So total resistance in first case, total resistance in first case is just equal to 2R by 3, right? Total resistance in first case is just equal to 2R by 3, and therefore what would be the power dissipated? So you can just say it is E square, okay, E square divided by this total resistance. In first case you can say it's R1, okay. So power dissipated in first case is E square divided by R1. So right now let's not substitute the value, we'll substitute that at the end. Next is the second case. What's the second case? So 2 from this A, section A, 2 bulbs glow and 1 from section B glows. So it's like this, right? 2 from these glow, 1 from the section B glows, okay. So this is R, this is R, they are in parallel. So the resistance of this parallel combination is R by 2, right? It's R by 2. So this is R by 2 and this is R. So you have R by 2 and R in series. So the total resistance in the second case, let's call it R2. So R2 is equal to R by 2, okay, resistance of these two, and the resistance of this one is R. So R by 2 plus R. So that is 3 by 2 R, okay. And power dissipated in second case would be equal to E square by R2. Therefore, if you take the ratio of P1 to P2, what do you get? P1 to P2 is, it's inversely proportional to R1 and R2, right? So this is R2 by R1, and that's equal to 3 by 2R, and divided by R1 is multiplied by its reciprocal, that is 3 by again 3 by 2r, 3 divided by 2r. So r gets cancelled. So it's 3 square, 9 divided by 2 square, 4. So it's 9 by 4. 9 by 4 is the answer. Okay. A filament bulb 500 watt, 100 volt means its power is 500 watt, and it needs potential difference of 100 volt is to be used in a 230 volt main supply. When the resistance R is connected in series, it works perfectly. Okay. So when a resistance of R is connected in series, so this is the bulb and this is the resistance. Okay, and this is 230 volts main supply, 230 volts, and the bulb consumes 500 watt. Okay, so it means that it gets whatever it needs, right? It needs 100 volt of potential difference and it's getting that. That's why it's working perfectly. And the question is, the value of R is, what is this R? Okay, so then let's suppose this is point A, this is point B, right? This is point B and this is point C. This is point C. So if bulb is working properly, how much should be the potential difference between A and B? It should be 100 volt, right? Potential difference between A and B must be equal to what? 100 volt. Okay, because it needs potential difference of 100 volt to work properly, and it's working properly means the potential difference across the bulb is 100 volts. Then you are supplying total of 230 volts and this one is getting 100 volts. That means what is potential difference across the resistance? It's equal to 230 minus 100 remaining. Okay, 130 volts, right? So V AC, you can say it's 230, which can be written as VAB plus VBC, and that's equal to 230, right? And what is VAB? VAB is 100. Okay, so it's 100 is equal to, sorry, 100 plus VBC is equal to 230. That means VBC is equal to 130 volts. Okay, so you got the potential difference across this resistance. Then what else can you get? So can you get the current? You can get the current. How? Because the power consumed by this bulb is equal to what? 500 watt, and you have potential difference. Okay, so either you can find out using that formula either you can find out the resistance of bulb because you have power and you have potential difference. So either you can make use of V square by R, right? Or because you have V as well as P, or you can make use of P is equal to VI and find out the current, right? So let's make use of P is equal to VI, and from that you get I equals to P by V, and that's equal to what? 500 divided by 100, right? So current in this branch must be 5 amperes. Okay, so current in this branch is 5 amperes. Same is the current in this resistance. Okay, so VBC can be written as the current multiplied by that resistance R, and therefore what is the resistance? It's VBC divided by I, and that is, what is VBC? So VBC is 130, I is 5, so it's 130 divided by 5. So it is 26, right? It's 26. So the answer is 26 ohms. It's option C. Got it? Yes, no? Okay, good. All right. So let's see another question. I'm sorry. So see, just based on the simple concept of power, lots of questions have been asked. Okay. All right. See this one. An electric kettle has two heating coils. When one of the coils is connected to an AC source, the water in the kettle boils in 10 minutes. Electric kettle has two heating coils. Okay. When you connect one coil, then water boils in 10 minutes. When other coil is used, the water boils in 40 minutes. If both coils are connected in parallel, then the time taken by the same quantity of water to boil will be. This is the question. Okay, so now suppose you need some heat, particular amount of heat to boil the water. So in first case, what you can say is heat is equal to V square upon R1 times T1. Okay, takes time T1, right? So then in second case, you can write that H is equal to V square by R2 times T2. Okay, so if we combine, if we compare this, so we get H and V would be equal in both cases, right? It provides same potential difference, and heat developed should be same in both cases. Okay, so what's the relation of time with the resistance? So time is directly proportional to R, right? Time is directly proportional to R. Yes, no? Okay, how? So you can see that. So first case T1 can be written as what? H by V square, H by V square times R1, right? Take that V square on this side, R1 on this side. So we get T1 is equal to H by V square times R1. So time is equal to some constant, because H is a constant, V is a constant. So it is some constant K times R1. Similarly, you can write T2 is equal to H by V square times R2, means it is K times R2. Okay, and now when you connect the two resistances in parallel, what will happen? Two resistances are connected in parallel. Okay, so then time taken in this case would be equal to what? That same K times Rp. Okay, same K times Rp. Okay, so what is Rp? Rp is R1 R2 divided by R1 plus R2. Okay, so you get T is equal to K times R1 R2 upon R1 plus R2, right? But we want to compare the time, not the resistance. We don't have resistance, right? So what we can do here is we know that 1 by Rp, 1 by Rp is equal to 1 by R1 plus 1 by R2. Okay, and we can multiply this whole equation by k everywhere, right? We can multiply this thing by k. So K times Rp would be equal to 1 by K times R1 plus 1 by K times R2. 1 by K times Rp is equal to 1 by K times R1 plus 1 by K times R2. Right? Why? Because we wanted to compare the time taken in these three cases. Okay. So this is time taken in third case. K times Rp is time taken in third case. So you have 1 by T is equal to 1 by T1 plus 1 by T2. Okay, So again you can say T is equal to what? We know the shortcut for this, it would be equal to T1 T2 divided by T1 plus T2. Okay, then you can substitute the values. What are the values? First it takes 10 minutes, then it takes 40 minutes, so it is 10 times 40 divided by 10 plus 40, so 400 divided by 50 means 8, so it takes 8 minutes. Okay, this one is clear, everyone? Let us see the next topic, that is Kirchhoff's laws. Okay, so let's see Kirchhoff's laws. So what are Kirchhoff's laws? So sometimes we encounter very complicated circuits, okay, and in order to solve them we need some shortcuts. Okay, so Kirchhoff's laws are shortcuts. Okay, so there are two laws. One is the Kirchhoff's current law, and what does it say? So see, suppose this is a point where n number of wires meet. Okay, so I1, I2, I3, I4 are the currents through those wires, right? So Kirchhoff's current law says that the algebraic sum of all currents at any junction is equal to 0. Okay, algebraic sum of all currents at any junction is equal to what? It's equal to 0. Okay, then what does that mean? So whatever charge is coming towards the junction, it must be equal to charge going away from the junction. The junction is that point where the wires meet, it will not store any charge. Okay, it will not store any charge, right? So then here current coming towards the junction is considered to be positive, or you can consider it to be negative. Then the current going away from junction would be positive, right? Current coming towards the junction you consider it to be positive, then current going away from the junction is considered to be negative, or vice versa. Okay, so let's consider current coming towards the junction as positive. So what can we write? We can write here I1 plus I2 plus I3 plus I4, I1 plus I2 plus I3 plus I4 minus I5, because this current is going away from junction, minus I6 is equal to 0. Right? So this is how we can apply the Kirchhoff's current law. And this KCL, Kirchhoff's current law, it is the law of conservation of charge. Okay, this is just the law of conservation of a charge. Okay, is this thing clear, everyone? It is quite simple, right? Next one is Kirchhoff's voltage law. Okay, next one is Kirchhoff's voltage law. So what does it say? It says that the algebraic sum of all potential differences and EMFs in a closed loop is equal to 0. Okay, the algebraic sum of all potential differences and EMFs in a closed loop is equal to 0. Okay, and this one comes from the law of conservation of energy. Okay, this one comes from law of conservation of energy, and there have been questions in the exam that Kirchhoff's current law is law of conservation of charge, something else, etc. Okay, so Kirchhoff's current law is law of conservation of charge, Kirchhoff's voltage law is law of conservation of energy. So it says that the algebraic sum of all potential differences and EMFs in a closed loop is equal to 0. Okay, so now see, sum of all EMFs plus potential differences means I times R, sum of all I times R's is equal to 0. So now suppose this is a circuit and we'll apply the Kirchhoff's voltage law to this circuit. So there are certain sign conventions to apply the Kirchhoff's voltage law. What are those? While tracing a loop in direction of the current, potential differences is considered to be positive. Okay, while tracing the loop in direction of current, potential differences are considered to be positive. The positive terminal of the cell appears first, then EMF is positive. Okay, while tracing a loop in direction of current, if you are in direction of current, going in direction of current, the potential difference is considered to be positive. And if positive terminal of a cell appears first, then EMF is also positive, right? So for an example, suppose you are going from A to B, okay, you have this branch and you are going from A to B and current is directed like this, then EMF is positive, E is positive. Why? Because you encounter positive terminal first. And what would be the potential difference in this case? So potential difference would be negative because you are moving in opposite direction of the current. Okay, you are moving in opposite direction of current. So potential difference in R is I times R, but since you are going in opposite direction of current, current is this way, you are going from A to B, therefore the potential difference you will take as minus IR. Okay, then if you consider this one, so here again you are going from A to B, but now you are going in direction of current. So in this case the potential difference would be positive. Potential difference is just equal to what? I times R. Okay, this is clear everyone? Right? Okay, good. So then now we can apply these laws. So for an example, you have the circuit. So consider this loop. Which loop? A, B, C, F, A. Okay, loop should start from some point and it should end at the same point. So A, B, C, F, A, this is the loop. So then you are going here in opposite direction of current. So current is shown this way. So when you go from A to B, you encounter positive terminal of the cell. So E1 would be positive, right? E1 would be positive. So you have E1. Then you are moving in opposite direction of current. So the potential difference here would be I times R1, but since you are going in opposite direction, so you write minus I times R1, minus I1 times R1. Okay, then you go from B to C, there is nothing. Then you have R3 and R2, but current is coming this way. Okay, this is I is the current in this branch, it's coming this way, you are going in opposite direction. Okay, so you have minus, okay, the potential difference would be negative. So minus I times these two resistors R2 and R3. Minus I times R2 plus R3 is equal to 0, right? And similarly, you can take another loop. So F, C, D, E, F, F, C, D, E, F. In this loop, you are going from F to C. So now you are moving in direction of current. So potential difference would be positive. So you have I times R2 plus R3. Okay, plus then you are going like this. So C to D there is nothing. Then again you are moving in direction of current only. So current here is I2. So the potential difference would be I2 times R4 and it would be positive. So plus I2 times R4, and then as you are moving you see the negative terminal of battery. So therefore the EMF would be negative, minus E2. Okay, therefore minus E2, and that's equal to 0, right? So this is how we apply the Kirchhoff's voltage law, okay, or the Kirchhoff's loop law. It's also called as Kirchhoff's loop law. Okay, first one is called as Kirchhoff's junction law, this one is known as loop law. All right, so this is theory. Let's see questions based upon this so that we'll understand it better. So Kirchhoff's first law, that is summation of I is equal to 0 at any junction, at a junction, deals with the conservation of. So what's that? Okay, option C is conservation of charge, right? Next one, Kirchhoff's first law and second law of electrical circuits are consequences of. First law means the junction law or current law, and second law means the loop law. Option C, conservation of electric charge and energy respectively. Correct. It's conservation of electric charge and energy. Next one, I'm sorry. Consider the following two statements. Kirchhoff's junction law follows from the conservation of charge. Kirchhoff's loop law follows from the conservation of energy. Okay. So both of these are correct, right? Both of these are correct. Okay. So both A and B are correct. So it's option D, right? So these questions were very simple. Let's see next one. So here, see the electrical circuit shown in the figure. Which of the following equations is a correct equation for it? So here we need to apply the Kirchhoff's law, right? So let's name this circuit. Let's call it something A, B, C, D, E, F, A, right? A, B, C, D, E, F, A. Okay. Then you have current I1 coming from here, I2 coming from here. At this junction, it combines, it's moving in same direction, right? So it combines, and current from here onwards would be equal to I1 plus I2. Let's call it I. I is equal to I1 plus I2. Okay. Then see the options. So if you see the options, in three options you have I1 plus I2, means either you need to take this loop or you need to take this loop first, and there are chances that you will get one of the options, right? Okay, what did I say? That in the options you have I1 plus I2. If you take this loop, there is no I1 plus I2. There is I1, there is I2. But if you take this loop or this loop, I1 plus I2 will come, right? If you take this loop or which one, or this loop, right? So let's take this first loop. In loop you have A, B, C, F, A. What does the KVL say? So we have I, right, which is equal to I1 plus I2 times R. Then it will be positive because you are moving in direction of current. Come to point C, and then you are moving like this. So current is like this. So again you are moving in direction of current only, and current in that branch is I1. Current in this branch is I1, and you see the battery. So negative terminal appears first. So you have minus E1 is equal to 0. Sorry, current in this branch is I1. I1 times, what would be the potential difference? I1 times R1. Okay. So you have I1 times R1, and then you see the EMF. So minus you have EMF, and that's equal to 0. Okay. But see whether it matches with any one of the options. So there is E2 in this branch, and this is our E1. This is E1, right? So it doesn't match with this one. Let's check this one and this one. So what is I? And here EMF is positive. So you can just multiply the equation with the negative sign. So you will have E1 minus I times R. What is I? It's I1 plus I2. Okay. And minus I1 times R1, and that's equal to 0. Right? You just have multiplied whole equation by negative sign. Okay. So right hand side doesn't change because it's 0, and we are multiplying the left hand side by negative sign. So this one will become positive, other two will become negative. Does it match? You have E1 minus I1 plus I2 times R, and minus I1 R1. Yes, it matches. Option D. This is the answer. Very simple. Okay, see next one. In the circuit shown, the cells A and B have negligible resistances. For VA equal to 12 volt, R1 is equal to 500 ohm, and R is equal to 100 ohm. The galvanometer G shows no deflection. Okay, galvanometer shows no deflection. the value of VB is. What's the value of VB? This is the question. Okay, so again let's write this thing as A, B, C, D. This point is E. Okay, F, A, B, C, D, E, F, A. And then let's apply the Kirchhoff's loop law in this loop and this loop. Okay, so current through the galvanometer is 0. That means current in this branch, let's say it is I2, it's equal to 0. So if that is 0, current in this branch is, let's say I, it splits at this point in I1 and I2, so that I1 would be equal to I, because current in the second branch is equal to 0. Okay, and then let's apply KVL in loop 1 or in the loop A, B, E, F, A. So this is the loop. Okay, so again you are moving in direction of current, so you have I times R1 plus, again you are moving in direction of current, so I times R, and then you have minus VA, and that's equal to 0, right? Or you can just say that VA is given, it's 12 volt, R is given, and R1 is given. Okay, from that we can just find out I is equal to VA divided by, because you can move this VA on other side, it will become positive. Then you can take I common from this term, so let me write it down. So it is I times R plus R1, and that's equal to VA. So you have taken I common, moved VA on other side, and then what remains is I is equal to VA divided by R plus R1, right? R plus R1, put the values. So you have 12 volts divided by what, 100 plus 500. So this is 600, or you can say 6 into 10 raised to 2. 12 by 6 will give you 2. Move 10 raised to 2 in numerator, so it becomes 10 raised to minus 2. 2 times 10 raised to minus 2 amperes. Okay. So then you want to find out what is VB. So in the second loop, in loop, what's that? B, C, D, E, B. Okay, in this loop, what can you say using KVL? Okay, using KVL, you can say B to C there is nothing, current is 0, that's why the potential difference in this one galvanometer is equal to 0. So you can say 0 times, or let's say I2 times resistance of galvanometer, whatever it is, and this thing is 0, okay, because I2 is 0. Then you see the positive terminal of battery, so plus VB, and then you go from here to here, there is nothing. Then I is coming this way and you are going in opposite direction, so you have minus IR, and that's equal to 0. So I2 is 0, so this term will become 0, and therefore what do you have is VB is equal to I times R. Okay, so just put the value. So I is 2 times 10 raised to minus 2, 2 into 10 raised to minus 2, and R is 100. Okay, so R is 100, and therefore what's the answer? This 10 raised to minus 2, 100 gets cancelled out. So answer is 2 volts. VB is equal to 2 volts. Okay, this one is clear. Now let's see the next topic, that is Wheatstone's bridge network. Okay, and what is Wheatstone's bridge network? So it's a circuit which looks like this. There are 4 resistances. This is P, this is Q. Okay, then there is this resistance called as R, this one called as S. So they are connected like this. Okay, and along the diagonal, along this diagonal or this diagonal, you will connect a galvanometer, right? Between these diagonal points you will connect a galvanometer, and between these 2 points you are connecting a battery having voltage equals to V, suppose. Okay, and to control the current you connect a variable resistance, it is called as rheostat. I'm sorry, you connect a variable resistance, it's known as rheostat. Okay, so then, so circuit looks like this. There are 4 resistances, one like this, one like this, one like this, one like this. They are connected in this manner, and then there is a galvanometer, okay, in this branch. Okay, now what does the Wheatstone say? He says that if this P by Q is equal to R by S, then this is known as a balanced network, and in that case the current through this galvanometer would be equal to 0. Okay, in that case the current through the galvanometer would be equal to 0, right? When P by Q, P divided by Q is equal to R divided by S, in that case the current through the galvanometer would be equal to 0. We say that the bridge is balanced. Okay, so we can see that how. So we can just apply the Kirchhoff's voltage law, right? So suppose this is point A, this is point B, this is C, this is D, and some current comes till point A, that current is I. Here it splits in 2 parts, I1 and I2. Okay, it splits in 2 parts, I1 and I2. At this point B, it further splits in 2 parts. Current through the galvanometer is Ig, and if Ig is subtracted from I1, what remains is I1 minus Ig, because current moving in this part is Ig, so what remains is current coming was I1, current going here is Ig, so what remains is I1 minus Ig. So I1 minus Ig goes this way, Ig comes this way, okay, and I2 comes this way. So this I2 and Ig combines, and the current in this branch would be I2 plus Ig, right? Current in this branch would be I2 plus Ig. Okay, so then you have I1 minus Ig and I2 plus Ig. So that minus Ig plus Ig gets cancelled out. So what remains is I1 plus I2, and that was the current coming to the point A, right? So the current at this point splits in I1 and I2. That means current I is equal to I1 plus I2. So here what current flows this point onwards? It is I1 plus I2. Okay, so it should be equal. Current coming out of the positive terminal should be equal to current entering the negative terminal of battery. Otherwise you have messed up something, right? So this thing is clear. Current division, is it clear? Okay, in loop ABDA by KVL, apply KVL. So what do you get? You go from A to B. So you have I1 times this resistance P. Okay, I1 times this resistance P. Then you are moving from B to D. So you have Ig times this resistance G, resistance of the galvanometer. Plus you move from D to A. But now you are moving in opposite direction of current. So you will have minus of I2 times of R. Okay, minus I2 times R, and that all should be equal to 0 by KVL. Okay, and then let's assume that Ig is equal to 0. So this second term will become 0. Move this minus I2 times R on other side. So you get I1 times P is equal to I2 times R. This is your equation number 1, let's say. Then see the loop BCDB. So in this loop you have I1 minus Ig times of Q. Okay, that is the potential difference in this one, I1 minus Ig times of Q. Then you are moving in opposite direction of this current. So you have minus of I2 plus Ig times S, minus of I2 plus Ig times S, and again here also you are moving in opposite direction of current. So minus of I2 times G, and that's equal to 0. Okay, again consider Ig is equal to 0. So Ig is equal to 0 here, here, here. So this third term becomes 0. what remains is I1 times Q minus I2 times S is equal to 0, and you can move this term on other side. So what do you get? I1 times Q is equal to I2 times S, right? So you have this first equation, then second equation. If you divide first by second, what you get is P by Q is equal to R by S. Okay, P by Q is equal to what? R by S. Right, this thing is clear, everyone? So if Ig is equal to 0, you get P by Q is equal to R by S. And what does that mean? It means that if P by Q is equal to R by S, then Ig would be equal to 0. Right? If Ig is equal to 0, you get this condition, P by Q is equal to R by S. And it means that if P by Q is equal to R by S, Ig would be equal to 0. Right? Okay, good. Then now we make use of this fact that P by Q would be equal to R by S if Ig is equal to 0. Okay, and we make a device known as a meter bridge. So what is a meter bridge? It's a device which is used to find out the unknown resistance. Okay, so it makes use of a wire having length equal to 1 meter. Length of this wire is equal to 1 meter. Okay, and then what else do you have? These are copper strips, 1, 2, 3, and in between this two copper strips, this one and this one, you connect one resistance, let's say R. Here you connect another resistance, let's say S, and then this you have this wire, okay, having length equal to 1 meter, and that's why it is known as meter bridge. Okay, length of this wire is 1 meter, and then between this point, at point B, what you do, you connect a galvanometer. Okay, and the other side of that galvanometer is connected to a stylus which you can slide on this wire. Okay, so you will slide that stylus on this wire till the time the current through the galvanometer would be equal to 0. Okay, this whole assembly, it's connected, A and C, it's connected to what? It's connected to a cell. Okay, so you slide it till the time, what happens? Current through the galvanometer becomes equal to 0. So you can see that this is just equal to, this is just similar to the Wheatstone's bridge network. How? Because you have this resistance and this resistance, right? So you can imagine them to be connected like this. This is one resistance, this is second resistance, and this is the wire. And you have the galvanometer, and you are sliding this stylus till the time current in the galvanometer becomes 0, right? So it means that this is a bridge network now, balanced bridge network. So resistance of this divided by resistance of this part, okay, R by S would be equal to what? It would be equal to resistance of this much part of the wire, okay, this part of the wire, divided by resistance of this part of the wire. So it's just like the bridge. Is this thing clear, everyone? Yes, no? Okay, good. So then you know that the resistance is directly proportional to length. Okay, the resistance is directly proportional to the length, and the balancing length here is equal to L1. What is the balancing length? So the length of left hand side, it is known as balancing length. Okay, length of this part. Suppose your stylus touches this point, so this one would be balancing length. So if this is L1, this length would be equal to what? 100 minus L1, because this is 100 centimeters. So the remaining length would be equal to 100 minus L1. Length of wire is 100 centimeter. Balancing length is L1, means the remaining length is equal to 100 minus L1, right? Okay. And then what we can say is this resistance by this resistance is just equal to resistance of this part of the wire divided by resistance of this part of the wire. So R by S is equal to resistance of wire. We know it is directly proportional to length. That's why here we can write some constant times L1 divided by same constant times 100 minus L1, right? So that kk will get cancelled, okay, and what remains is R by S would be equal to L1 divided by 100 minus L1, okay. R by S is equal to L1 divided by 100 minus L1. So then out of R and S, let's say one resistance is known, one resistance is unknown. So what we can do is, using this condition, we can just find out the unknown resistance, right? This thing is clear, everyone? A resistance wire connected in left gap of a meter bridge balances a 10 ohm resistance in the right gap at a point which divides the bridge wire in the ratio 3:2. If the length of the resistance wire is 1.5 meter, then the length of 1 ohm of the resistance wire is, okay, so what does it say? It says that resistance wire, there is a wire connected in left gap of the bridge, meter bridge. There is just this wire, okay, it will have some resistance. And what's there in the right gap? There is a resistance. Let's say this is R, this is S, S is equal to 10 ohm, okay. So it balances against this 10 ohm resistance, right? And the balancing length that you get, is 3:2. So it is 3:2, okay. So length of this part is, what would that be? This is 60 centimeter and this would be 40 centimeter, right? So 60 by 40 is 3:2, okay. So therefore what you can say is R by S is equal to 3:2. And what would be R? Just move S on that side, so it's 3 by 2 times S, and that is 3 by 2 times of 10, right? So it is 15. R is 15, okay. R is 15 ohms. Then what does the question say? If the length of resistance wire is 1.5 meters, length of this wire is also given, it is 1.5 meters, then the length of 1 ohm of the resistance wire is, okay, what would be the length of 1 ohm, okay. So how can we find it out? So total resistance is 15 ohm, total length is 1.5 meters, right? So you know resistance is directly proportional to length, okay, resistance is directly proportional to length. And then, so resistance is, suppose, some constant times length, and what do you want? Suppose R dash is 1 ohm, this is given, R you found it's 15 ohms, what would be L dash? This is the question, okay. You can just say R dash by R is equal to L dash by L, okay. R dash by R is equal to L dash by L, right? And what would be L dash then? Just move L on this side, so you get L dash is equal to, L prime is equal to R prime by R times of L. So what resistance do you want? You want 1 ohm, okay. So R prime is 1 ohm. What is R? R is 10, no, R is 15, right? So multiplied by, what's the length? Length is 1.5, okay. So 1.5 divided by 15 means it is 0.1, right? It's 0.1. So this is the answer, 0.1 meters or 10 raised to minus 1. So it's option B. Is this one clear, everyone? Right. So a simple question, okay. This is from NEET 2020. Let's see next one. The meter bridge shown is in the balance position with P by Q is equal to L1 by L2. If we now interchange the positions of galvanometer and cell, will the bridge work? If yes, what will be the balance condition? So what's given? You have this meter bridge, and they say that P by Q is equal to L1 by L2. Okay, so it's just like you have P by Q equals to R by S. Suppose resistance of this one is equal to R, resistance of this one is equal to S. Okay. Now, if you replace galvanometer with a cell, so you connect cell in this branch, you have this P, here you connect cell. So you can connect it like this, or you can connect it like this, it does not matter, right? Here you have connected a cell. Okay, you have this P and Q, and this length is L1, this length is L2. So between the 2 points where you had connected galvanometer, you are now connecting the cell, right? Now you are connecting, you're now connecting the cell. Okay, and then between the 2 points where you had connected the cell, now you connect the galvanometer. Okay, now you connect the galvanometer. So will it work? This is the question. Okay, so here you are connecting the galvanometer. So let me draw it by red. So this is the galvanometer. Will it work? Actually it will, right? Okay, so it will work because see what you have done is here the balancing condition. Okay, for this bridge network to work, what would be the balancing condition? Balancing condition here would be what? P by Q has to be equal to what? Again, it should be equal to L1 is to L2 only. That's it. Same thing, right? P by Q has to be equal to L1 is to L2. Right? So it works. Okay. So the answer is P by Q has to be equal to L1 by L2. What you are doing is actually you have, suppose, a bridge network. Let me explain it this way. You have bridge network. This is your bridge network. Okay. So if you interchange the galvanometer and battery, so if you connect galvanometer in this branch, what condition do you have? P by Q is equal to R by S. If you connect galvanometer instead in this branch, then what should you have? Okay, for this branch it's P by Q should be equal to R by S. In this branch it should be P by S is equal to Q by P by R is equal to Q by S. Okay, and you can see if you do P by R is equal to Q by S, means if you connect galvanometer here, it should be P by R is equal to Q by S. Okay, it's the same thing as that of P by Q is equal to R by S. How? Just move this Q on this side, R on this side. Okay, right, you can do that interchanging. Okay, this R, if you move on this side, it will go to the numerator. If you move this Q on this side, it will go to the denominator. So it's same as that of P by Q is equal to R by S. Is this thing clear? So even if you interchange the galvanometer, the bridge will work and the balancing condition will be same. This is the answer. Is it clear, everyone? Yes, no? Tell me. Right, Selva Kumar? Okay, good. All right. Let's see next one. The resistance in the two arms of meter bridge are 5 ohm and R respectively. 5 ohm and R respectively. When resistance R is shunted with equal resistance. Now, what do you mean by shunted? Shunted means equal resistance you are connecting in parallel. Shunt means parallel. Shunt means what? Parallel. Okay. Then the new balance point is 1.6 L1. So first the balance point is L1. Then when you shunt this resistance, means you connect another resistance in parallel, then the balance point becomes what? 1.6 L1. The resistance R is, what is the resistance R? Okay, so this is simple. So in first case you have 5 by R equals to L1 divided by 100 minus L1, right? And in next case, when R is shunted, means another R is connected in parallel. R is shunted by R, then the resistance in left gap would be still the same, it's 5 divided by resistance in right gap would be R by 2, okay, and that's equal to, now what's the balancing length? So they say that the balancing length becomes 1.6 L1. So it is 1.6 L1 divided by 100 minus 1.6 L1, right? So this 2 is in denominator of denominator, so it will go to the numerator here, and then it will go here in the denominator if you want to move it on that side. So it will be 5 by R will be equal to what? 1.6 L1 divided by 2 times of 100 minus 1.6 L1. So this will be your equation number 2. Okay, this is clear. Okay, good. So then you can equate 1 and 2. So what do you get? 1.6 L1 divided by 2 times of 100 minus 1.6 L1, and that's equal to L1 divided by 100 minus L1. Cancel out L1 and L1, okay, and then take that 1.6 on that side, okay, and then what we can do is we can write this thing as 2 times of 100 minus 1.6 L1, it's equal to 1.6 times of 100 minus L1, okay, and then you can find out L1. So this thing would be 200, or let's multiply again by 10. All right, 200 minus 3.2 L1 is equal to 1.6 times 100 means 160 minus 1.6 L1, okay. So then move this 160 on this side, so that's 200 minus 160 is 40. 40 is equal to move 3.2 L1 on that side, so it becomes plus 3.2, right? 3.2 minus 1.6 is 1.6 L1, and then we can multiply this equation by 10. So 400 would be 16 L1. So L1 is equal to 400 divided by 16, okay, or 100 by 4. That means 25 centimeters. So we got L1 equals to 25 centimeters. So if L1 is equal to 25 centimeters, you have 5 by R, right? 5 by R is equal to 25 divided by 100 minus 25 means 75. So what would be R? That implies R is equal to what? So this is 1/3. Okay, so 5 times 3 means 15, right? This is clear? Yes, no? Okay, not a difficult problem. I messed with calculations here. Okay, nothing difficult, right? Anyways, so this is meter bridge. Now let us see some problems based on the Wheatstone's bridge. Okay, so let's extend for 10-15 minutes and we'll complete this, right? So this one is from NEET 2023. So let's see this problem. The magnitude and direction of current in the following circuit is. So that's very simple. You have these two batteries and they are connected like so as to oppose each other. Okay, if you connect negative positive, then negative positive, then the two batteries will help. Here they are connected in such a way that so as to oppose each other. So what would be the total EMF in this circuit? total EMF would be equal to E1 minus E2, and that's equal to 10 minus 5, so it is 5 volts, right? And what is the total resistance? Okay, before that, so now we want direction of current also. So this battery, if you see the positive terminal, it will send the current in this way. The second battery, if you see its positive terminal, it will send the current this way. So which current would be greater, current sent by 10 volt battery or 5 volt battery? Current sent by 10 volt battery, right? And therefore what would be the direction of current? It will be like this or like this, towards right or towards left? Tell me. See, this is a bigger battery. No, this is a bigger battery. No, this is 10 volt battery, sends the current like this. Bigger battery is sending the current towards right. Smaller battery is sending current towards left. So you can consider this current. This current would be of course larger than this one, and net current would be, let's say this is I1, this is I2. The net current would be equal to what? I1 minus I2, right? And it will be towards right because this one is larger battery. This is its positive terminal. Is it clear, everyone? Right, Nikita, is it clear? Okay, good. Then you just have to find out the total current. So what's the total resistance? R is equal to 2 ohm plus this is all in series, 2 plus 7 plus 1, so that means 10 ohms, and therefore I is just E divided by R, so that is 5 by 10 means 0.5, right? 0.5 amperes. And it goes from what? In this direction, means it goes from A to B. Okay, it goes from A to B through point E. So that's the answer. It's option B. There is no other 0.5, so you don't even need to think about that. You just find out the total current and that's the answer. Okay, in this case. But they could write 0.5 ampere. They could give this another option from B to A. Okay, that would be wrong, right? Okay, so this is simple. Then let's see this one. The net resistance of the circuit between A and B is. So there have been questions like this. So you have this bridge network. You can see that, and instead of galvanometer, what's connected there? You have connected a 7 ohm resistor. So the trick to solve this kind of question is see if the bridge is balanced or not. If the bridge is balanced, then even if you connect some battery here, there would be no current flowing through this branch. So if there is no current flowing through this branch, means it is ineffective. Okay, the branch is ineffective, right? But let's check whether it is ineffective. Okay, so let's check if P by Q is equal to R by S. What is P? P is 3. What is 4? What is Q? Q is 4, right? What is R? R is 6. And what is S? S is 8. So P by Q is 3 by 4. R by S is 6 by 8, right? And it is 3 by 4. So it matches, right? Okay. Therefore, bridge is balanced. Because the bridge is balanced, this branch is ineffective. So therefore, you can neglect that branch, and then what remains is a simple circuit. So this is A, you have 3 volt, 3 ohm, then you have 4 ohm. So this is 3, 4, right? And what is this thing? This is 6 and 8. So you have 3 and 4 in series and 6 and 8 in series, but this and this in parallel. What is this thing? This is 7. What is this thing? 8 plus 6 is 14. So you have 7 and 14 in parallel. what's the total resistance? Rp would be equal to 7 times 14 divided by 7 plus 14. That's simple. So what's that? Okay, this is 7 times 14, means I can say this is 3 times of 7. Okay, and in numerator you have 7 times 14, right? This is 7 plus 14, no. So this is 3 times of 7. This is 21, means 3 times of 7. Then you can cancel out this 7 and 7. So what remains is 14 by 3. So the answer is 14 by 3 ohms. This is very simple, right? Okay, good. Let's see next one. The resistance of each arm of Wheatstone bridge is 10 ohm. The resistance of 10 ohm is connected in series with the galvanometer. Then the equivalent resistance across the battery will be. Okay, so we have same Wheatstone's bridge. Let's take the Wheatstone's bridge. Okay, get rid of currents. Right. So you have this Wheatstone's bridge network, and you are connecting an extra resistance here in series with the galvanometer. This is 10, P is 10, Q is 10, R is 10, and S is 10. This is given, and this resistance is also 10. So now this is a balanced bridge network, right? Because this is 10, 10, 10, 10. Okay, 10 by 10, P by Q would be equal to R by S. So whether you connect something or not in this branch, it doesn't matter. What would be the resistance across this battery? So just neglect this branch. Okay, just neglect this branch. This is ineffective. Okay, and then what remains is this thing, PQ and RS in parallel. Okay, just like this one. And now tell me what would be the resistance. This is 10, 10, 10, 10. 10, 10 means 20, 20 and 20 in parallel. Two identical resistors in parallel. So what's the resistance? Rp would be just equal to R by 10, right? 20 by 2, sorry, R by 2. That's 10, right? So answer is 10 ohm. This is clear. It's like you have two identical resistors in parallel. Okay, 10, 10 means 20 and 10, 10 means 20. Two identical resistors in parallel. So what is the equivalent resistance? Remember the formula, n identical resistors in parallel. So it is R by N. Okay, this is clear, Selva Kumar. Okay, good. Let's see next one. Okay, so again you can remember it this way also. If you have four identical resistors connected in the bridge network, then what is the equivalent resistance of bridge network? So it's just equal to any one of those resistance. Okay, if instead of 10 you have R here, then what would be the equivalent resistance of this thing? It will be 10, means it will be equal to R, right? Yes, no? Okay, and that is precisely this next question. In a Wheatstone's bridge, all four arms have equal resistance R. Equal resistance is connected in all four arms. Okay, if the resistance of galvanometer arm is also R, the equivalent resistance of the combination as seen by the battery is, it is R, right? Okay, equal resistances are connected in four arms, then what would be the equivalent resistance? It's just equal to R. Okay, this is clear. We have just seen this. Okay, good. Then let's say this one, let's see this one. For the network shown in the figure, the value of the current is, okay, so first of all find out equivalent resistance. Before that, check whether the bridge is balanced or not. Most of the times it is balanced only. Okay, so you don't need to do anything. Otherwise, what will you do? If the bridge is not balanced, then you will need to apply the Kirchhoff's laws, right? Then you will write this is A, B, C, D. Okay, then this is I, it will split in two parts, I1, I2. Again, that I1 will split in two parts. Okay, that business you will have to do. Okay, but let's check whether this one is balanced or not. Okay, so we have P by Q is equal to 4 by 2, right? 4 by 2, and R by S is equal to what? It's 6 by 3. So this is 2 by 1, and this is also 2:1. So it is balanced, right? So that means this is ineffective branch. So remove that resistance. So what remains is 6 ohm, and this is 9 ohm, right? 6 plus 3. So they are in parallel. So Rp would be equal to, okay, resistance in upper branch, in this branch is 6 ohm, and in this branch it is 9 ohm. So 6 times 9 divided by 6 plus 9 means 18 divided, no, yeah, correct, sorry. 6 times 9, okay, 6 times 9 divided by 6 plus 9. So how much is that? 15. Okay, 6 times 9, then you can divide that by 5, and this thing would be 3. 6 threes are 18, 18 by 5. So Rp is 18 by 5 ohms, right? And you want what's the current? So it is this voltage, its value is not given. So let's just take V divided by the total resistance. So what's the current? It's V divided by Rp. That is V divided by 18 by 5. Move that 5 in the numerator. So it is 5 by 18 times of V. That's the answer. 5 by 18 times of V. Option D. Okay, this one is clear. Yes, Nikita. Good. Let's see next one. In the circuit shown, if the conducting wire is connected between points A and B, wire is connected between these 2 points, the current in this wire will be, okay, will there be any current in this wire? So the answer is, if the bridge is balanced, then there won't be any current. If bridge is not balanced, then there would be some current. Okay, so let's check whether the bridge is balanced or not. So it is 4 by 4. Okay, P by Q is equal to what? 4 is to 4. That's 1 is to 1. But then R by S is 1 is to 3. So not balanced, right? Not balanced. So there will be some current. Okay, then the question is whether the current will be from B to A or from A to B. So for that, this is B. Same potential difference is applied to this branch as well as this branch, right? So check current in which branch would be more, right? So what would be current in this branch? So it will be V by 8. The total resistance here is 8. Current in this branch is I1. Let's say it is I1. Current in this branch is I1. And that I1 would be equal to V divided by 8, right? Total resistance is 8 if this wire is not connected. And current in this branch would be what? I2. It will be V by 1 plus 3, that is 4. Okay, then you tell me current in which branch is more? I2 is more, right? Okay, I1 is equal to V by 8, I2 is equal to V by 4. So I2 is greater than I1. Right? So how will the current flow if you connect these two? From here to here, from, yeah, A to B or B to A? B to A, right? It will flow from B to A. Okay. It will flow from B to A, right? So answer is current will flow from B to A. Okay, so this is one way of understanding this. There is another way. Just find out potential of this point and this point, right? See, potential of this point is A. Actually, sorry, this is A and B, no? So let's say this point is C. Potential of this point is same. Okay. Now see what potential drop will be there. So I can say what will be the potential of A. So VA would be equal to potential of point C minus some current. Okay, VA would be equal to VC minus current is I1. I1 times what? I1 multiplied by this resistance, 4 ohm resistance. Okay, so that is equal to, that's equal to Vc minus what is I1? So I1 is V by 8. V by 8 times 4. Okay, so what's that? This is V by 2. Okay, Vc minus V by 2. So when you go from this point to this point, the potential difference decreases by what? V by 2. Okay, potential of this point is Vc, potential of this point is how much? Vc minus this much potential difference. Okay, potential difference in this resistor, and that's equal to V by 2. What about point B? So when you go from point C to point B, okay, then the potential difference decreases by Vc minus I2 times of this resistance. This resistance is just 1. Okay, so that's equal to Vc minus I2. What's I2? So I2 is equal to V by 4. V by 4 times 1. It's just V by 4, right? So then current decreases, sorry, voltage decreases just by V by 4 here. Okay, and the voltage decreases by V by 2 when you move from Vc. When you move from point C, the voltage decreases by V by 2 here. That means the potential of point B would be greater than that of the potential of point A, and that's why the current will flow from B to A. Okay, so not like this because I2 is greater than I1, because if you just make this thing, I guess 3 ohms, if you make that 3 ohms and this one 1 ohm, still the current would be same, right? But then the potential will decrease by what? It will decrease by 3 by 4. Okay, so then this one would be at lower potential. The current will flow like this when you connect those two. Is this thing clear, everyone? Okay, so since the potential of B is greater than potential of A, the current flows from B to A. Okay, so since VB is equal to VB is greater than VA, current flows from B to A. So that's the answer, right? Okay, then let me check how many 2 questions are there. Let's solve one more. I will leave one for you. 3 resistors PQR, each of 2 ohm, are unknown resistance and unknown resistance S form 4 arms of a Wheatstone's bridge circuit. When a resistance of 6 ohm is connected in parallel to S, the bridge gets balanced. Okay, so you have this bridge. Let's take a bridge. Okay, so they say that PQR and PQR are 2 to 2. Okay, but then when a resistance of 6 ohm is connected in parallel to S, when a resistance of 6 ohm is connected in parallel to S, this is S, P is 2, Q is 2, R is also 2. okay. R is also equal to 2, but S is something else. But when you connect 6 ohm resistance, then the bridge gets balanced. What is the value of S? This is the question. What is S? So it's simple. If bridge is balanced, then all remaining 3 are 2 to 2. That means this parallel combination must be equal to 2, right? So Rp must be equal to 2, okay. So what is Rp? Rp is equal to 6 times S divided by 6 plus S, and that's equal to 2, okay. R1 R2 divided by R1 plus R2, okay. So 6 times S divided by 6 plus S, that's equal to 2, and therefore what is 6S? 6S is equal to 2 times 6 plus S times 2, 2S. So move that 2S on this side. So you get 4S is equal to, right, 6S minus 2S, 4S is equal to 12, and that means S is equal to 3. S is equal to 3 ohm, right? It's option A. This is clear, everyone? Right. So then we'll stop here. So this is the end of current electricity. I hope you solved some problems, okay, from homework problems. There was one more topic earlier called as a potentiometer, and that has been removed, okay, that has been removed. So this is the end of electricity. Tomorrow we'll start with the next chapter.